This is the second web talk in the Mplus Webtalk series. Webtalk number 2 discusses latent transition analysis and the new technique of random intercept latent transition analysis. It focuses on how to use Mplus for this type of analysis, giving details about how to specify the models in Mplus and how to interpret the results from the output and how to understand the error messages. In contrast, Webtalk number 1 focused on modeling ideas and relating different models to each other. Webtalks number 1 and 2 are related in that the modeling ideas used in Webtalk 2 were presented in a larger context in Webtalk number 1. Webtalk number 2 uses a series of new Mplus features designed specifically for latent transition analyses. And these features were introduced in Mplus version 8.5 and much more extensively in version 8.6 in order to make the interpretation of the analysis results easier. Following APA conventions, this web talk can be referred to as shown here. And I'd like to thank my Mplus colleagues for their help in putting this talk together. On slide 2, you get the website for Mplus Web Talks and links to the YouTube videos. And again, a companion piece of this talk is Mplus Web Talk number 1, where LTA and RI-LTA analyses are discussed in segments 11 to 14. Slide 3 gives the outline of the whole web talk, and it's a web talk that's broken up into over 20 segments, each of them about 10 to 15 minutes long. So you can go and find the topic of particular interest to you easier. I start off with an example. So I'll discuss a particular data set and focus on the kinds of questions you can ask in latent transition analysis, trying to be as non-technical as possible. In contrast, section 2, the basic statistical building blocks section, goes deep into the technicalities of the statistics behind the latent transition analyses. And you may want to study that right away or come back to it once you've gotten into the analyses. I'll start off with analysis without covariates, where I'll talk about regular LTA and RI-LTA, the new random intercept version. I'll compare results from those kinds of analysis, and I discuss how to decide on the number of classes using those two approaches. Then I'll turn to checking model fit and model modifications, trying to make the model fit better. So I'm going to check response pattern fit and bivariate fit. I'm going to look at the typical assumption of measurement invariance across time. And I'm going to investigate whether we have to add residual correlations across time. And I'm going to take a look at lag 2 modeling, using that instead of the typical lag 1 modeling. Then I'll add covariates, and I'll focus on covariate effects on transition probabilities, where we have some new nice output features. I'll again talk about how to do that in the RI-LTA context, and I will compare results with the regular LTA. Then I'll turn to the interesting topic of measurement invariance across individuals. So that has to do with concepts like item bias. I'm going to take 2 approaches to study measurement invariance across individuals. One is the typical multiple group analysis, and the other is the approach of using direct effects of covariates onto indicators. And I'll discuss why I think that's preferable in this case. Then I'll turn to special topics: modeling stationarity of transition probabilities, mover-stayer modeling, and a long section on distal outcome added to the latent transition model. And then finally, I'll turn to error messages in a long section discussing the typical error messages that you get when using multiple latent class variables as in latent transition analysis. And I'll just discuss first a little bit about maximum likelihood theory for identification and non-identified models. Finally, and what didn't fit on this slide, I'll make some final comments about this type of modeling in general. We'll now turn to an example that will give you the substantive types of questions that you can ask in the latent transition analysis setting. So that'll be a motivator for all the different methodologies that we're going to try out in this web talk. So one single example is going to be used throughout the whole web talk. And the example has to do with reading proficiency. We're going to use data from the early childhood longitudinal study, equals K, with a nicely sized sample of 3,500 children. And we have 4 time points: fall and spring of kindergarten and fall and spring of grade 1. We're going to consider 5 binary items as the latent class indicators, and they represent the mastery of or proficiency in basic reading skills of letter recognition, beginning sounds, that is the sounds of beginning letters of words, ending sounds, sight words, that is words that a child can recognize without thinking through the various letters. And we have words in context, the most advanced proficiency of these 5. We're going to hypothesize that there are 3 latent classes corresponding to 3 stages of learning: low alphabet knowledge, early word reading, early reading comprehension. We're going to use a covariate. It's a binary covariate poverty, indicating whether or not the child's household is below or above the US Census poverty threshold. And this analysis draws on the analysis in Kaplan 2008 in developmental psychology, where you also see references to the data collection and the creation of the 5 binary items. Turning to slide 5, here you have a prototypical LTA. You have 2 time points, and for each time point we measure these 5 indicators, and for each time point we have a latent class variable, C1 for time 1, C2 for time 2. And we're going to consider 3 parts to this model: a measurement part, initial status part, and a transition part. The measurement probabilities describe the relationship between the latent variable, latent class variable, and the indicators, the observed indicators. And we can express that relationship in terms of the probabilities, because these dependent variables are categorical binary. So we have an LCA, or latent class analysis, for each time point. And we are going to assume typically that the measurement characteristics here are the same across time. Second part is the initial status. What are the probabilities of the latent classes in the beginning of this repeated measurement situation? Third part is the transition probabilities. How does C1 influence C2? How do changes in latent class membership at time 1 get turned into latent class probabilities at time 2? What are the probabilities for staying in the same class versus moving to another class? Now, there are many variations on this basic theme. You may want to study, for instance, measurement invariance across time. Does it hold very well or not at all for some of the items? You may want to bring in covariates, like the poverty covariate, that can then have an effect on the latent classes as well as an effect on the latent transitions. By that covariate, you can also divide the sample in this case into 2, poverty and non-poverty, and do a kind of a multiple group or 2-group analysis to study measurement invariance across individuals with respect to the poverty covariate. You can also have direct effects from the covariate to the latent class indicators, and in that way establish whether or not you have measurement invariance across individuals. Furthermore, you can have a distal observed outcome that is observed later on in time, and we will see towards the end of our web talk how you handle those kinds of distal outcomes and model them as a function of the latent class memberships and the transitions. Finally, we're also going to talk at the end of the web talk a little bit about a model called a mover-stayer model, where movers are following a regular LTA and the stayers are individuals who have probability 1 of staying in the same class and therefore probability 0 of transitioning to a different class. Slide 6 shows then the first part that we talked about, the measurement part of the model, and this is derived from an analysis using regular LTA with 4 time points. So we have the 3 latent classes, and they are the 3 columns in this table, and the 5 rows are the 5 items, the latent class indicators, measuring these latent classes. And the entries are probabilities, conditional probability of getting letter recognition correct. If you're in class 1, it's about a 50% chance of getting that right. If you're in class 2, it jumps up to 99%, and in class 3, it's certain that you're going to get that right. Now, looking at the beginning sounds item, you have a very low probability of getting that right in class 1, but a very high probability of getting it right in class 2. So that's a good discriminator between being in class 1 or 2. Likewise, ending sounds has an almost 0 probability in class 1, whereas it's sizable in class 2 and almost certain in class 3. Likewise, sight is a very discriminating item. It doesn't get sizable until you belong to class number 3 of early reading comprehension. Then you get the sight word item correct. Now this is those probabilities are held equal across all time points in a baseline type of model, and this output is provided under the heading latent class indicator means and probabilities for each latent class. Second part is perhaps the most important one, having to do with the transitions, hence the name latent transition analysis. Now we're going to consider a transition matrix for only the first 2 time points, although the analysis is based to a 4 time point analysis. So we're going to consider transitioning from fall of kindergarten to spring of kindergarten. So the latent classes are then both the columns and the rows. So we're saying for those who started in fall of kindergarten in class 1, you have a 34% chance of staying in that class, 65% chance of moving on to class 2, which is desirable, and a very small chance of jumping all the way to class 3 in spring of kindergarten. If you belong to class 2 at the start of kindergarten, you have almost 0% chance of falling back, of unlearning what you knew at the end of kindergarten. You have a sizable chance of staying in the same class at the end of kindergarten, and you have a bit of a chance to move on to class 3 at the end of kindergarten. If you're fortunate enough to start in class 3 in kindergarten fall, you're certain to stay there at the end of kindergarten. So you see this characteristic of zeros in the lower triangular part of the matrix, so that people move forward and don't fall back. And this transition table, transition matrix, is provided under the heading latent transition probabilities based on the estimated model. Now here we put together the time 1 probabilities, time 2 probabilities, and the transition probabilities. So let's see how to read this. So the rows are the latent classes, and here we have the probabilities at time 1 for the latent classes. So we have a fairly high probability of being in the lowest class in the fall of kindergarten, and a sizable probability also for being in class 2, but a very small probability of being in class 3 already in the fall of kindergarten. And then we have the transition matrix, those probabilities that we just looked at here in the middle. And from those two quantities, we can then compute the time 2 probabilities for the 3 classes. That is, the probabilities for the classes in the spring of kindergarten. And how do we do that? Well, if you look here, we can ask ourselves, how can we end up in class 1 at time 2? C2 equals 1. Well, we could start time 1 and stay in time 1. Start at class 1 and stay in class 1. That's this product, that probability. And another possibility is that we start in class 2 and fall back into class 1. Very small chance, but we write it out here. Or you could start in class 3 and fall all the way back to class 1 with 0 probability. If you add these up, you get the value 0.235. And you can ask, how do you end up in class 2? Well, you can start in class 1 and move over to class 2 here, make that transition with this probability, this product. Or you can start in class 2 and stay in class 2, or start in class 3 and move back to class 2, but that happens with probability 0. Adding that up, you get the value that we have in the right column. How do you end up in class 3? Well, you can start in class 1 and move to class 3, low probability however, or you can start in class 2 and move to class 3, you get that term, or start in class 3 and stay there. And if you add those up, you get the probability here. So this is saying that knowing time 1 probabilities, the initial status probabilities, and the transition matrix, you get time 2 probabilities as a result. It's not a separate type of parameters here, they follow from the other parameters. Those who like matrix algebra, they would see this as a vector, row vector multiplying a matrix, giving this vector. This is provided in the output under the heading Final Class Counts and Proportions for each latent class variable based on the estimated model. On slide 9, I show another interesting way of looking at the data using latent transition analysis. We're going to take a look at typical transition paths. And this is for regular LTA with 4 time points. And in the table here, I give you the estimated frequencies for the 3 most frequent paths through the latent class variables across the 4 time points. So here are the paths. 1, 2, and 3 are the rows. And the time points are fall of kindergarten, spring, kindergarten, fall of first grade, spring, first grade. And here are the number of people and the percentage of the total sample size. So the most common transition path is starting in the lowest class in fall of kindergarten and going up to class 2 in the spring of kindergarten. And then over the summer, not much happens, and they stay in class 2. Whereas they move over to the desirable class 3 by spring of first grade. So 33% follow that pattern. Second most common pattern is that the child starts in class 2 already in the fall of kindergarten, stays in that class through kindergarten and at the beginning of first grade, and then moves over to class 3 in the spring of first grade. 13% follow that. Third most likely class, starting at class 2 and already in kindergarten moving up to class 3. Staying in class 3 then throughout first grade. 10% of the kids do that, according to regular LTA. This kind of information is interesting and is provided in the Tech 15 output under the heading Final Class Counts and Proportions for the Latent Classes based on the estimated model. Now we turn to basic building blocks in the outline. That's going to give some technical background for the analysis that we're going to carry out. And you may study this now, follow along, or go back to it and learn about it in more detail once you've seen more applications and feel more motivated. So here are the statistical underpinnings. A very useful statistical technique is logistic regression, which uses a loaded parameterization, and that can be used for different kinds of dependent variables, binary, ordinal, or nominal dependent variables. We're also going to talk about probabilities and odds ratios. Odds are ratio probabilities, and it refers to a single variable, categories of a single variable, relating them to each other. Odds ratios refers to a relationship between two variables, and it's a ratio of odds. Now the Mplus modeling uses this loaded parameterization to estimate the parameters of the model. But given that those loaded estimates may be a bit difficult to interpret, we also provide output that contains probabilities, odds, and odds ratios. Now turning to slide 12, talk about sampling distributions of these quantities. And by sampling distribution I mean what you get, for instance, in a Monte Carlo study when you take repeated samples from a hypothetical population and estimate a certain parameter, and you get then a distribution over the different replications of your Monte Carlo study. So often we get normal distribution or approximately normal distributions, and that's the case for logits, for the coefficients that come from logistic regression. And they have a chance to vary in a normal fashion, given the fact that the parameter values vary from -infinity to +infinity, like a normal distribution does. So maximum likelihood estimation assumes this approximate normality, at least in large samples, and therefore you typically see these symmetric confidence intervals, where you take the estimate and then take ±1.96 times the standard error to get the upper and lower limits of the 95% confidence interval. Now in contrast, probabilities vary from 0 to 1, and therefore will be likely to have non-normal distributions. And for non-normal distributions, you need to use, or you should use, non-symmetric confidence intervals. And by a non-symmetric interval, I mean that the distance between, let's say, the lower limit and the estimate is different from the distance between the estimate and the upper limit. So that's in contrast to the regular confidence interval here, which uses 1.96 times standard error for both the lower and the upper limit. Odds and odds ratios vary from 0 to +infinity, and we note then that 1 is the neutral point. That is when there is no, for instance with odds ratios, when there is no relationship between the two variables. They have non-normal distributions as well, so you need to use a non-symmetric confidence interval also there. So in this case then, you have significance if the confidence interval does not contain 1, the neutral point. Now non-symmetric confidence interval limits for odds and odds ratios can be obtained directly by exponentiating the confidence interval limits of the logits, where the logits are normally distributed. So you take the normal distributed, the limits of the normal distribution for that logit estimate, and then exponentiate the upper and the lower limit. We're going to get into detail of that further on. And thereby you get non-symmetric confidence interval. So this is done systematically through the Mplus output. Here then on slide 13, I give you a quick reminder of logistic regression. So for the figure top left, x-axis corresponds to a continuous x variable, x2. Let's say that it is h. And the y-axis has to do with a binary dependent variable u. Let's say it is cancer or not. And the issue is that we want to, for a binary variable, u equals 0 or 1, model not the values but the probability of the events. So we want a regression curve that varies between 0 and 1, like in this picture. So you have then a symmetric curve here, and you can choose many different kinds, but we're going to work with the logistic curve. So we have a logistic regression. U is a binary dependent variable, and we pretend that we have a binary covariate x1 and a continuous covariate x2. So cancer, smoking, and age. So we see that the probability of having a cancer increases with age, and it also increases as a function of being a smoker or not. So for any given age, you have this lower probability of cancer for non-smokers, x1 equals 0, and a higher one for x1 equals 1 for the smokers. So to get this S-shaped curve, we write the probability of u equals 1, having the cancer, as a function of the x values for individual I, as this logit function. And this is something that you can actually compute on any kind of calculator. And the logit is then this linear expression with the intercept beta 0, slope beta 1, and slope beta 2. So this, what's in parentheses here, is called the logit. And that's linear. So you have drawn that picture up in the top right corner here. Now, two examples then here is that the dependent variable can be a binary latent class indicator, an observed variable, and x1 can be a binary latent class variable, so a latent variable instead of an observed dummy variable like smoker, non-smoker. And x2 can be a direct effect from a covariate. That would be an example of how you use logistic regression. You will see that example later on when we talk about measurement non-invariance across individuals. Another example is when the dependent variable is a latent class variable. So the dependent variable is unobserved with two classes, and x1 and x2 are covariates predicting this latent class variable. You may also have only one binary variable. So say that you only have x1, and say that u is a latent class indicator, and you have no x2, but you have an x1, which is, say, a binary latent class variable. And then we're talking about the measurement model in a latent class analysis that you also use for latent transition analysis. So in this case, there is no x2, and you just have 2 points on the logistic curve here, 2 points, probability values, which are ruled by the logistic curve. Another general comment here is that these curves are parallel whenever, and these curves are parallel, these lines are parallel, whenever you don't have an interaction between x1 and x2, as over here. When you have an interaction between them, then the curves will be non-parallel. So we'll use that technique in several instances here. Now, we talked about the case of a binary dependent variable. How do you generalize that to more than 2 categories and to unordered categories? Because we have different models for unordered and ordered categories. Ordinal variables versus nominal variables. Well, you can note then that you can rewrite this expression that we looked at, the logit regression that we looked at, in this case for only one x, to write it in a different form, algebraically equivalent form, but in a form then that can easily be generalized to more than 2 categories. So here you have then a regression of a nominal variable u with r categories on a covariate x. And you're then looking at multinomial logistic regression. So you have an expression for a certain category r of the capital R possible categories for u in the numerator here, and in the denominator you have the sum of these exponential terms over all of the R categories, R minus 1, up to the last category, R, which gets the value 1 because the last category is the reference category, so that both the intercept A and the slope B are 0. That is, you have e to the power of 0, which is 1 according to mathematics. So you get that 1 as the last category. Now an odds ratio then is easily computed from this multinomial logistic regression. You just take the exponent of this slope b for the x, and they represent an odds ratio, which is the odds of being in category R versus the last category for a certain x value x divided by the same odds for an x value x minus 1. So for instance, you have for a binary x equals 1 versus x equals 0. So the odds ratio is the ratio of an odds for x equals 1 divided by an odds for x equals 0. Now this same multinomial logistic regression formulation is used for regression with a latent nominal latent class variable as a dependent variable. So if we look at that on slide 15, as an example we have C1 regressed on x, that is the latent class variable at time point 1 in the latent transition analysis. So here then, instead of a u, we have this nominal latent nominal variable. Latent class variable is nominal, and we write it out multinomial logistic regression in the same way as on the previous slide, and in the same fashion the odds ratio is e to the power of b for category R, representing the odds we just talked about. Now very often then, as we will see, it's useful to change the reference class from the last class to the first class or some other class. And to do that, to change it from the last to the first, you subtract the logit for the first class so that the logit becomes 0 for the first class. So you have then the for particular category R, you subtract from the intercept A1 and subtract from the slope B1, and you do that throughout like that. That's how you change the reference class. Now this is of course not something you want to do by hand, but it's computed, it can be computed in the Mplus model constraint command, but it also can be done automatically by reordering the latent classes, as is now easily done in Mplus since version 8.5. On slide 16, I'm talking more specifics about reordering latent classes. So say that we have this reading example, and we would like to see the classes in the order low reading skills, medium, and high, in the order that we have seen them in the example. And let's refer to them then as class 1, class 2, class 3. So let's say that we do an Mplus run, and Mplus doesn't know which order we want the classes to come out. So say that the run gives us the order medium, high, low. So the order is class 2 comes first, class 3 comes second, class 1 comes last. So now we want to reorder that to get it in the desirable order of low, medium, high. So we reorder the order 2, 3, 1 that we have up here to 3, 1, 2. That is, we want the last one, the third one, to come first, to put 3 there, and we want the second one, the first one appearing, we want that to come second, so we say 1 here because it's the first one there, and we want the second appearing class to be last, so we put 2 there. That gives you the order low, medium, high. Well, you probably prefer your own way of thinking about how to do this. Here's how I usually write it out when I reorder. This is done using opt-seed from the first run and s-values, where you give this order 3, 1, 2, which is the order that you want. And you can do this for one latent class variable as I show here, or for several as you would have in latent transition analysis. And we're going to see examples of the case where you have several of them. This reordering can also be done to highlight different parts of the modeling. For instance, if you have the example of C1 regressed on the binary X variable poverty, and you have the case of low, medium, high, high being the reference class, then say that you have that in your output, that order, then the odds ratio for C1 class number 1 on poverty turns out to be 8.1 something, and with this 95% confidence interval. So it's significant. That is, it doesn't cover 1. It's way above 1 for the lower limit. And we're saying then that the odds of being in the low class relative to the high class at time 1 is much higher for poverty 1 than for poverty 0. It's 8.101 times higher. That is the order that we got from the reordering. Now, if you keep the order of the first run, which is the medium, high, low order, that could be of interest too, where low is the reference class. So we're saying then that the odds ratio for being in class 1 of C1 in the regression of on poverty, that odds ratio is 0.232. It's also significant, does not cover 1, that is, the interval does not cover 1, and it's just happened to be lower than 1. So we say that the odds of being in the medium class, which is the first one here, right, relative to the low class at time 1 is much lower for poverty than not being in poverty. Let's take an example of logistic regression here. Distal outcome in latent class analysis. And we're going to look at odds ratios and their non-symmetric confidence intervals. So we have 5 latent class indicators and the latent class variable C and a covariate X that predicts the latent class probabilities, but also predicts a distal outcome U. So say that it's a binary variable. So U is in this case regressed on 2 variables, on X and on C. One is observed, the other is latent. One is binary, the other is nominal. So let's see how we deal with that. So on slide 18, we're going to look at odds and odds ratios with 2 predictors. So the general case, we're going to work from logit regression. Logit is the same as log odds, as we will realize as time goes on here. The log odds for U, that's one way of writing the logit model. You just focus on the logit, which, as we said before, is a linear expression in the 2 x's. So the odds ratio interpretation is this, namely the OR for x1. The effect of x1 is e to the power of b1, and that's irrespective of the value of x2. And the OR effect of x2 is e to the power of b2, irrespective of the value of x1. And that's a function of using the logistic regression equation. Probit regression doesn't have this feature. So that's very valuable, that the effect of x1, the odds ratio for x1, that is the relationship between x1 and the dependent variable u, is not dependent on the value of x2. So you can control for x2 and compute this effect of x1 separately. Latent class model, if you look at that now, instead of having 2 observed x's, we have 1 observed x and 1 latent x, namely C. Then you have logit regression with x and the latent class predictor C. So it's log odds for u conditional on x and C being in a certain class. So we then put a subscript for the intercept and not a subscript for B in this case, because we're saying that there is no we're saying that the intercept of u can vary as a function of c, but the slope of u on x does not vary as a function of c. We have no subscript c on b here because we don't have an interaction between x and c. You could have c have an arrow, broken arrow to the arrow from x to u, and that would say that the regression slope u on x could vary also with c, but not in this case. Now in Mplus we don't talk about intercepts in logistic regression as much as thresholds. And thresholds, we call that t here, is the negative of an intercept. Doesn't matter if you work with the intercept or threshold, it's just a change of the sign. Now the odds ratio effect of x is e to the power of b, irrespective of the latent class, by virtue of using logistic regression, just like we talked about up here. Now the odds ratio effect of the latent class variable c, the other predictor of u, is expressed in terms of the u odds for c equals 1, the first class, divided by the u odds for c equals c, the last class. Just like we have talked about before, using the last class as a reference class. And again, it's not influenced by the value of x. So let's say here on slide 19, how would you express this in Mplus if you wanted to get into the technicalities of it? Let's look at that odds ratio effect for the latent class, that is the latent class effect on the distal outcome u. So we have the Mplus script here, x equals poverty, and u being begin item from the reading data at wave 2, and the latent class indicators are the 5 binary reading indicators, letter recognition and words in context from time 1. So we have time 1 indicators and corresponding latent class variable predicting a distal outcome at time 2. So in the variable command then we have the use variables as the poverty covariate and the latent class indicators, letter recognition to words in context, and then the distal outcome. And we're saying that the indicators and the distal outcome are categorical. And as before, we're looking at 3 classes. We do a mixture type of analysis with a moderate number of starting values and processors equal to 8 to make it go faster. And the model is, in the overall part, we regress C, latent class variable, on poverty, the X variable, and we regress begin 2 on poverty as well. And putting this regression up here in the overall means that it is held equal across the different classes of C. So there's no interaction between C and poverty. And then in class 1, you put in the distal outcome threshold, begin 2, threshold 1, it's a binary variable, and label it T1. And then you have the latent class indicators, the thresholds of which you want to vary across class 2 and across class 3. And in all 3 classes, you label the threshold for the distal outcome, T1, T2, T3. And then in the model constraint command, you define these new parameters, probabilities, odds, and odds ratio. And for instance, at the poverty level of 0, you compute the probability of being having the probability of the outcome for class 1, for class 2, and for class 3, corresponding threshold values varying from T1 to T2 to T3. So that's the probability of getting the beginning item right at wave 2 for the 3 different classes. And the odds are then the ratio of the probabilities P1 divided by its complement, getting it wrong, 1 minus P1, and odds for 2 and odds for 3. And we're interested in the relationship between the classes of C and the binary outcome of begin 2. So we're looking at then the odds ratio, or the ratio of odds being in the first class relative to the odds of being in the last class. So that's an odds ratio that tells us the relationship between the latent class variable and the distal outcome. And we have then the odds ratio computed that way. We have a non-symmetric confidence interval that we want for this odds ratio. And we base that on the estimate and the standard error of the log of the odds ratio, namely the log odds 1 minus the log odds 3, because the log of a ratio is the difference between the two log odds. So the log of odds 1 divided by odds 3 is the log of odds 1 minus the log of odds 3. And we know that the odds here for the log odds rather for each of the three categories is the threshold. It's only the threshold that influences that, or rather the loaded. So it's the minus the threshold, and the difference between that and the minus of the T3 comes out here. So the difference is minus T1 plus T3. And if you compute this for, this was for power t equals 0, if you do that for power t equals 1, you get the same diff 13, same odds ratio value, because the slope for B cancels out. And that's how it should be, right? The relationship between C and the distal outcome should not vary as a function of x, that is the x values. That's what we agreed on. So there is a technical description of the details of these calculations, and you of course get help by Mplus in terms of doing this automatically in the output. But here's what's going on. And there may be situations where you have to do this, which are sort of non-standard, where you have to do this yourself in model constraint. Here you have a template to go by. Now, we then want to continue here by saying that we want to have the non-symmetric confidence intervals by exponentiating the confidence limits of the loaded difference for the distal outcome. We said that the estimated odds ratio was minus, or rather the estimated difference, which is the loaded difference, is minus 0.948 with this standard error. And a symmetric 95% confidence interval for this loaded difference is therefore minus 9.948 plus minus 1.96 times the standard error. So you get the confidence interval like this, which is for the loaded difference. Now, to get to the odds ratio confidence interval, well, first of all, the estimate is the exponentiated value of the loaded difference. So that's minus 0.948. That's used in the e to the power of. The non-symmetric confidence interval is then computed by exponentiating the limits. The exponentiated lower limit of the loaded difference and the upper limit. So the confidence limits will be these two values. And we see then that that doesn't cover 1, and therefore the value 0.388 is considered significant. So the odds ratio, that is the influence of the latent class variable on the binary distal outcome, is significant. And in this case, we're lucky that the Mplus Outputs shows these results automatically under the heading Latent Class Indicator Odds Ratios for the latent classes. So there you have it. And that's as technical as we will get here now in the section Basic Building Blocks. On slide 21, we're going to take a look at another kind of logistic regression. We will consider the regression of C2 on C1, that is the latent class variable at time 2, related to the latent class variable at time 1. Now this is going to be a nominal dependent variable. C2 is nominal. And the predictor, the independent variable, is also nominal, C1. But we're going to still be able to work within the logit regression framework and the logit parameterization. So here you have a table that's familiar to you from the end of chapter 14 in our user's guide. You have the 3 classes as rows for latent class variable C1, and the 3 classes, the columns corresponding to the classes of C2. And you have A and B logit parameters in the table. We recognize the Mplus notation here as bracket C2 number 1 for the intercept A1 as the first intercept of the dependent variable C2. And then we have a second intercept A2, which is referred to this way. And then we have the 4 slopes, B11 to 22, which are the on statements. So C2 number 1 on C1 number 1 is B11, etc. down. And this is the Mplus parameterization using the A and B loaded parameters, where the last class is the reference class in all situations here. The shorthand specification of this is saying C2 on C1. That gives you all of these 6 parameters in one statement. The intercepts and the slopes, just like we do in regular regression of y on x for a continuous y. But sometimes it's important to be able to refer to each of the individual components like we do here. On slide 22 then, we take a little closer look at what C2 regressed on C1 actually means in its details. And drawing from regression analysis with a continuous y, we're looking at the distribution of y given x, that is this conditioning notation. And now, since we have a categorical dependent variable, C2, we're going to talk about the probability of C2 conditioned on C1. So what is that going to mean? Well, we're still in the logit parameterization. We're still in the last class as the reference class. So this is the transition table once again for the logits. Now, the way to look at this, given the fact that we condition on C1, we can take a look at each value of C1 separately. That is each row of C1. And each row is a multinomial model. That is, we have 3 different outcomes of a categorical variable. So in principle, there are 3 probabilities, actually 2 probabilities, since the probabilities have to add to 1. So 2 independent parameters. So that's the way to look at C2 given C1, 1 for each row of C1. For example, consider the A2 plus B21 in the first row and the second column. What does that mean? Well, that loaded expression can be translated into a probability for C2 equals 2, given that C1 equals 1, by the multinomial expression where we put in the exponent the loaded A2 plus B21 in the numerator, and in the denominator rather, we have these different exponential expressions for all of the 3 categories, where the last one is 1 because of the loaded zeros, and e to the power of 0 is 1. Now we're going to talk about odds in connection with these tables, and the odds then is a ratio of probabilities as before. So we have the ratio of the probability of being in this cell 2 and 1, that is up here, relative to the probability of being in the last class while still in the first class, that is the first row of C1. And I claim that that's e to the power of A2 plus B21. That is, we have the ratio of this expression divided by, that's the probability here, divided by the probability in the denominator, C2 equals 3, given C1 equals 1, which is e to the power of 0, which is 1. So, but with the same denominator down here. So if you take the ratio of those two probabilities, the denominator cancels out, and all you get left is e to the power of A2 plus B21 with divided by 1. So it's just that expression. So that's the odds of transitioning from class 1 to class 2, that is this probability, divided by transitioning from class 1 to class 3, from class 1 to class 3. So that's how you think about these probabilities. They're talking about a transitioning, and now we have them for two different C2 classes. That odds of transitioning from class 1 to class 2 versus transitioning to from class 1 to class 3 is going to be very high for the reading example. That is, it's very unlikely to transition to class 3 going from class 2, much more likely to transition to class 2. This is, after all, in kindergarten, going from fall of kindergarten to spring of kindergarten. In other cases, it may be more of interest to compare not to the last class, but to the class that corresponds to staying in the same class. That is 1, 1, 2, 2, and 3, 3, the diagonal. Now, you can do this by a change of reference class from the last class to the stayer class, the diagonal. So you have 0 lotus on the diagonal of the transition table. So what you do then, to get that to be 0, you subtract the term we had on the previous page, namely A1 plus B11. So that becomes 0, and then you subtract that A1 plus B11 from both of these two columns. Same thing for row 2, subtract A2 plus B22, etc. Just showing this in detail. So this is suitable for considering the odds of transitioning from class 1 to class 2 versus staying in class 1. This is a stayer. So that may be of more interest in the reading data example. That is, you want to know what the odds is to actually move forward in your reading knowledge from class 1 to class 2 versus staying in class 1. Now this kind of display, these kinds of odds are produced automatically in the output. So you don't have to worry about it, but this is how it's done internally. And sometimes maybe you want to do it yourself for some reason. So here's an example then from the reading data, transitioning from class 1 to class 2, that is fall to spring kindergarten. So we have this transition matrix for the first two time points that we looked at before. So we have the probability of staying in the same class is 0.338. Moving from class 1 to class 2 is 0.649. So a healthy probability of moving on to higher knowledge of reading. If you translate these probabilities then to odds for each row, you have the odds 1 for the diagonal class here everywhere, so that thereby you can see that that's a reference class. And here you get the odds of 1.920 for moving from class 1 to class 2. And that's computed as below here, shown here. The odds of transitioning from class 1 to class 2 is the ratio of 0.649 up here to 0.338. That's the odds of transitioning, 1.920. So you have a healthy odds, almost odds of 2 times higher probability of transitioning to the second class versus staying still at the first class. And then behind the scenes, Mplus computes the 95% confidence interval, a non-symmetric confidence interval as is suitable for odds, as we've talked about before. Now sometimes you want to calculate these transition probabilities for different covariate values. When you bring in covariates into the model, like the poverty covariate in the reading data, you might want to have these transition probabilities computed for specific values for many cases several covariates, maybe at the means or at specific values. Earlier versions of Mplus, this was called the LTA calculator, but now we call it more generally just a calculator. So that's available from the Mplus menu. That is, if you're in the output, in the Mplus editor's output, you have a menu, pull-down menu, where you can then see the word calculator showing up. And if you click on that, in this case, you get a window which says covariate values for conditional probabilities and odds of the latent class variables. So then you have a list of covariates, in this case only one, poverty, and you click on assign value and you enter, say, 1 and apply that, and then you get poverty is evaluated at the value 1, and then we click on OK and we get our transition probabilities and the odds for that particular poverty value. So here on slide 26, you see then the calculator in action. So this is regular LTA, the 4 time points, and you have C regressed on X. For poverty equals 1 and 0, and transitioning from C3 to C4. So these are the last 2 classes, and class variables, the last 2 time points I should say. So you have poverty equals 1, poverty equals 0, and you're interested in the transition from C3, which is fall of first grade, to C4, spring of first grade. So you have the rows being the starting classes and the columns being the ending classes for the 2 different values of poverty. So here are the values. And for instance, we can take, since we're at the end of the 4 time points, we might be interested in the movement from the second class to the third class, the desirable class at the end of spring first grade. For those classified as the family being in poverty, you have the probability of staying in class 2 is 0.226, moving from class 2 to class 3, 0.76. Whereas if you're not in poverty, then you have a lower probability of staying in class 2 and a higher probability of moving on to class 3. That is a more desirable outcome. So you have then the odds ratio here. Why is it an odds ratio, not an odds? Well, that's because now we're looking at the relationship between 2 variables, how the poverty covariate influences a transition. So now you have the ratio 0.764 divided by 0.226. That's the odds of moving for those in poverty, and divided by the odds for moving 881 divided by 115 for those not in poverty. So the odds of moving on for poverty is 3.381, so it's lower than 7.66, which is the odds for poverty equals 0. So the odds ratio is 0.44. So you have a low odds ratio. So you say that the odds is 0.44 less for poverty equals 1 than for poverty equals 0. So this is produced automatically in the output with confidence intervals, the non-symmetric confidence intervals for the odds ratios. So we see in the next slide, here's the output from Mplus, odds ratio output for effects of the poverty covariate. So now we have a transition table odds ratio. So whenever you have an odds ratio as opposed to an odds, we know that we're talking about the relationship between 2 variables. And here then you find that number 0.440, which is the odds ratio for the effect of poverty on transitioning from class 2 to class 3. And the interpretation is given explicitly here. The odds of transitioning to the third class at time 4 relative to staying in the second class is 0.440 times lower for power t equals 1 than for power t equals 0, and significantly so. OR 0.440, and here's the confidence interval. So we say that the odds, not the odds ratio, but the odds is lower, 0.44 times lower for power t equals 1 than for power t equals 0. So this is given in the output under the heading Covariate Effects on Transition Probability Odds Ratios. We will now turn to analyses using Mplus. And we're going to start without covariates, that is in the reading data. We are not going to use the poverty covariate, but only the 5 latent class indicators at each of the 4 time points. So we have 20 binary observed variables. And we'll start with regular LTA, which I discussed the ideas of in the example section up here, which is in segment 2, slides 3 to 9, and also discussed in more technical detail within the basic building blocks section. So focusing on regular LTA, let's take a look at actually running Mplus. And we will first take a look at how you specify HTML style output, which provides an easy way to navigate through the output via links. And we're going to find where we see the replications of the best log likelihood shows up and take a look at error messages. We're going to note the number of parameters, log likelihood, and the big class probabilities and entropy. And then as a first step, we're going to interpret measurement parameter results in the probability scale, because we want to assure that we have the latent classes in the order that we want them to be for interpretational purposes that we find being the best for the actual application. And if not, we're going to turn to the new feature of automatic class reordering, which was introduced in version 8.5, and that uses opt-seed and a new s-values feature, and I'll show you how you operate with those. This is described also in the Mplus version 8.5 language addendum, which you find where the user's guide is posted. And then we're going to interpret class and transition probability results in odds and odds ratio scales and take a quick look at some of the technical output. Now you can go to outputs 1 and 2 for this Webtalk, which you find at this address. I'm going to get there in a different way. I will take a look at Mplus here. And first of all, I'm going to show you the Mplus menu, the drop-down menu, where you see these options of using the plain text output, which many of you use, I think. But I'm going to work with the HTML output, as I mentioned. And you can click back and forth here, and the selection will stay. And this is what you do before you do the analysis. Now let's open the first analysis. So the file type here is HTML. And we're going to take a look at the regular LTA output. And you note then that you have these backwards and forwards arrows that we're going to use, and you have these magnifying glasses where you can make the font smaller or bigger, or the third one here resets the zoom to normal, no zoom. The fourth one is sets the current zoom level as a favorite, and the fifth one jumps the zoom level to your favorite zoom level, that is if you want to use it on the next output. So let's take a look at the input instructions here. I'm not going to go through the basic parts of Mplus input, except to note that we have a title, data, and variable command. And use variables here specifies the 20 binary variables at time point 1 with suffix 1, time point 2, time point 3, time point 4. That's the order in which they are given. And we declare all of them as categorical. And then we have the 4 latent class variables, C1 through C4. All of them have 3 classes. That's our hypothesized number of classes. And we're going to do a mixture analysis. And we're going to choose a modest number of random starting values to ensure that we find the global maximum for the likelihood. And you note that I have these numbers divisible by 8, that is the number of processors that I use on my computer. So in the first stage optimization, you're going to get 10 sets of iterations per processor, and in the second last stage you're going to get 2 per processor. So you see that arranged and activated on your screen output as the optimization starts. It doesn't have to be divisible by 8, but it's nice. And you notice then that the ratio between the second and the first is like approximately 1:4, which I tend to use. And then the model is, in the overall part, you regress C2 on C1, the Latent class variable at time 2 on the one at time 1, C3 on C2, C4 on C3. And then you get into the time-specific model statements, model C1, model C2, model C3, and model C4 here at the bottom. And the binary latent class indicators are these letter recognition at time point 1 to the words in context time point 1 with 1 threshold each because they are binary variables, and we give them parameter labels 1 through 5. There are 5 parameters listed in this list. If you look at the list of the use variable part, you see that they are listed consecutively. So that list corresponds to 5 parameters. And we let them be different. We let those thresholds be different at the second, for the second class, you give them different labels, and for the third class. But these numbers, 1 through 15, get repeated across all the other 3 time points to ensure that we specify measurement invariance across time. And then we can choose various output here. I typically work with Tech 10 and Tech 15 for a latent transition analysis. And you can take the back arrow, come back up here, and it's always good to look for input errors and warnings, and there are none. And we actually then below that have the summary of analysis, which is always good to look at. Sample size here, 3,575, that's right. Number of dependent variables should be 20, 5 times 4. And there are 4 latent class variables. And we use maximum likelihood with a robust estimation of the standard errors. Now we may want to take a look at the univariate proportions, but we're not going to do that now. Instead, let's go to model warnings and errors, that section. That starts with the random starts that we have done, the analysis, the various analyses for different starting values, and their log likelihood values are listed here. And you see that the best log likelihood is replicated throughout all of those. So we have a nice stable solution. And we see then that second column is the seeds. So this value we're going to remember for reasons that will become apparent. And below that we see that the best log likelihood has been replicated, and it says rerun at least twice the random starts. You don't have to do that because we already have a good set. Otherwise we always print this out, so you can end up in an infinite loop here doing this otherwise, if you don't ignore it. More importantly, you have this error message, which is very common. That is that the thresholds get fixed at very large values corresponding to probabilities of 0 and 1. So that's innocuous rather, and actually it's not bad at all. It's preferable that probabilities become 0 and 1. It often makes the interpretation easier. A more important message is this: one or more multinomial loaded parameters were fixed. To avoid singularity of the information matrix, you do not want singularity of the information matrix, because then you don't get any standard errors. Now it's listed then what the problems are. We're going to take a look at that, and we're going to see that in this case that's also innocuous. It corresponds to 0 transition probabilities, but we're going to wait a little bit with looking at the details of that. And then you come down to this part of the output. Chi-square test cannot be computed. That's has to do with frequency table tests with Pearson and log likelihood ratio chi-squares. I'm going to talk about that later on in the Webtalk. Model fit information. Here you note then how many parameters you have, what the log likelihood value is, and I tend to focus on VIC, rounded up to, don't include the decimals there. There are enough digits anyway. And then I look through the final class counts and proportions for each latent class variable based on the estimated model. We have simplified the output, moved some of the other output to the technical parts of the output, so to keep it clean. And you want to look at this first here to see that no classes have exactly 0 people or proportions in them. So this looks healthy, and we notice that we have a high entropy here. And then below that comes, as the next thing that you want to look at, latent class indicator means and probabilities for each latent class. And here, since we have binary latent class indicators, these are probabilities. So you have letter recognition, begin sounds, ending sounds, cite and words in context. And you have the 3 classes. And here then we note that the first class has high probability for getting the item right, except for the last 2 items. So that looks like, for those of you who followed through the example in the beginning, that looks like the second class, medium proficiency. This then corresponds to the low class because you have very low probabilities to get the item right, that second category here. So that's the first class, that is the low class. And the third here has high probabilities almost all the way down to the more advanced item, and therefore that's the high class. So we have them ordered as medium, low, high, where we want them as low, medium, high. So we want to reorder here before we go on and interpret things. You don't want to look at latent transition results for classes that are mixed up in their order this way. It's just hard to interpret. So we want to put the class that appears second, this one, we want that to come first, and the class that appears first, we want that to come second, and the class that appears third should stay third. That means that the reordering should use the numbers 2, 1, 3. That is, second class should come first class should come second, and third class should come last. 2, 1, 3. So we're going to remember that, and then the opposite as well, for doing the reordering of the classes before we go on. So that means we're going to go to output number 2 in HTML form, regular LTA reordered. Here you have it. And how do the input instructions change them? Well, the only 2 things that change is that now we work with the opt-seed option here. So not asking for a bunch of random starting values, but just the optimal starting value set that gave the best log likelihood. There were several of them, but we just picked the top one. And here's the number that we were looking at before. So you give that number, and the only other thing you do is give these S values, the 2, 1, 3 order at all 4 time points with that bar in between of the time points. You could, for another application, you don't have to have the same number of classes, and you can even use this for latent class analysis where you have only one latent class variable, so you only have one of these sets. And then I tend to ask for Tech 8 as well, because I want to be sure that the optimization is done, gets to the same log likelihood value that the initial run came to. The reordering of classes does not change the best log likelihood value, nor does it change the number of parameters. So let's take a look at that then, going back up and going to Tech 8. So you have them first an optimization, log likelihood, the apps change in the log likelihood over the iterations. They should always be positive. And it comes to this value. That looks like the likelihood that we had before, given in scientific notation. And then you have the reordered optimization, and it reaches the same log likelihood value here. So the reordering has worked here. There will be situations where it doesn't, so you have to look out for that. So then we go back up to the top here, and let's take a look at what else we want to see. We are back at the warning, so we're going to say something about this. These are 1, 2, 3 parameters that are fixed, and we're going to see why in a second. Here we have the model fit information. Sorry, jump by. And we have the same log likelihood, same number of parameters. And now we have the latent class proportions given here in a good order. So at time point 1, fall of first grade, 69% are in the lowest class, 28% in the medium class, and only 2% in the highest class. And that changes then over the time points, so that at the end of first grade, only 4% are left in the poorest class, lowest class, and 81% have moved over to the desirable class. So let's look then to verify also that the class reordering worked. So this should be the lowest class. So we see the low probabilities for category 2. So the items are 0, 1, but they get reordered as 1, 2, 1, 2 per Mplus default. So second class then should have low values for the last 2, and it does. And the third class has higher values for the last 2, which it should have. And these profiles, these probabilities are the same across the time points, because we have measurement invariance here imposed, and you can check that they are the same. And then we can finally go down to latent transition probabilities based on the estimated model. So here you have C1, C2. So the rows are the classes that you're in fall of first grade, and the columns are where you are in spring of first grade. So you have a 34% chance of staying in the lowest class, but a 65% chance to move from the lowest class to the second class through the kindergarten year. And some kids are in the second class when they start and stay there with a fairly high probability. Fewer of them move on to class 3 already by the end of kindergarten. So those are the transition probabilities. Now you can ask, well, is this really significantly different from that? And how do you measure that? Well, what statisticians tend to do is, instead of looking at probability differences, they look at odds, the odds of being in second class versus the first, which is just a ratio of those two probabilities. And you have them here then, that ratio. So here it is, transition table odds for C1 to C2. And you compare, in this table, you compare to the diagonal. So the reference class is the diagonal class 1, 1, 1. So looking at the first row, and we go through this in detail in the basic building blocks technical section. So this 1.92 is the ratio of those two probabilities that we just looked at here, 0.649 divided by 338. But now we also get the confidence interval, 95% confidence interval for this, going from 1.751 up to 2.104, which does not include 1. Hence, this is a significant odds, significantly greater than 1. And this is a non-symmetric confidence interval, which is what you need to have for odds, also for odds ratios, and for probabilities also, for that matter, because they don't have normal or symmetric sampling distributions. So here you have the odds for moving on, almost an odds of 2, that is 2 times higher probability to move on than staying in the same class. And then you can look and interpret all the other odds here up to down here say this is moving from fall of first grade to spring of first grade, and you compare to staying in the same second class here versus moving on to the third class during this first grade. And the odds are pretty good for moving on to the second class, 6.543. And once again, the 95% confidence interval does not include 1, so it's significant. Now we also have in 8.6 C-specific classification results. So for each latent class variable, you get an entropy, 88 for the first, and you get these classification logits that we use for multi-step estimation in WebNote 21. And so 89 here, a little higher for second time point, 88 again, and 93 highest for the last time point. We have good classification there. What else do we want to look at? So let's see here. You get the model results. Now in version 8.6, I really wanted to rearrange things in the order that an applied person wants to look at things, to learn about things. So the model results, which is what usually comes first, are given here in the usual logistic regression type of parameterization. So you look at logits, which are not always easy to interpret. Going from logits to thresholds in logit form to probabilities, it takes a little conversion in your head. Likewise, when you look at the regressions here, C2 on C1, it's easier to look at measurement probabilities and transition probabilities, and therefore I prioritize that in the output in this case, as opposed to other Mplus situations. Now, let's take a look at some of the other things. Tech 15 here has several subsections, and we're going to focus on final class counts for the latent classes based on the estimated model. So here you have the latent class patterns. So here is a child that stays in the lowest class throughout the four different time points. And here's one that moves to class 2 at the end. So the entries here are classes, and there are 4 time points. And here you have the most common path throughout the years, or the 2 years, the 4 time point. Starting in the lowest class, move to second class at the end of kindergarten, stays there over the summer to the fall of the first grade, and then moves to class 3 by the end of first grade. 33% of the subjects do that. So that's where we find the information in the table that I talked about in the example section. Let's see, is there anything else that we want to discuss? I think that's it for these 2 runs. So here we are on the outline analysis without covariates still, and now we're going to turn to RI-LTA, random intercept latent transition analysis. And here you have the model figure. We have the usual latent transition analysis model here at the bottom, but now we're adding a factor, a continuous latent variable, and we're going to think of that as a random intercept. It's going to have mean 0, variance 1, and it's going to have different loadings for each of the latent class indicators per time point. But those loadings, factor loadings, are going to be the same across time point. So that's the specific feature here. So this is described in detail in this article that's forthcoming in Psychological Methods in 2021. It's also described in Mplus Webtalk number 1. The modeling ideas are contrasted with the regular LTA modeling ideas. So this factor F, it captures time invariant between subject differences. Time invariant between subject differences. So that's often referred to as trait differences in psychology, and in psychometrics you might want to refer to it as measurement non-invariance. That's constant over time. Measurement non-invariance referring to the fact that the probability of an outcome of a latent class indicator giving latent class is different for different individuals with different F values, which also influences the latent class indicator outcomes. So because you have differences across individuals in the conditional latent class indicator probabilities, you have measurement non-invariance, and it's a constant one across time. On slide 32, we say a few more words about what this means and what the consequences are of using RI-LTA. So it turns out that in all the examples that I've seen so far, it fits the data much better than regular LTA, which seems, in retrospect, unnecessarily restrictive and gives distorted results. So the idea here is that you have longitudinal data, which is really a two-level model of time within persons. And in any two-level model, you would at least have a random intercept somewhere, if not also a random slope. So that's the idea here. We are adding finally a random intercept to this latent transition analysis model. And thereby, we don't have this confounding of between and within subjects' sources of variation. So these transitions represent a within subject process where we have gotten rid of time invariant between subject differences, which are up here, influencing the outcomes, but not influencing the latent classes. And by this, the latent class indicators correlate over time beyond what's captured by the latent class correlations over time. In regular LTA, you have correlation between U11 and U21, for instance, only because C1 influences C2. So you have this indirect connection between them. But in the random intercept version, the U11 and U21 indicators correlate also because they have the common cause, the factor F. So because of that, it tends to reduce the probability of subjects staying in the same class over time as compared to regular LTA, where you can think of part of the staying in the same class tendency is due to individuals' trait values influencing the outcomes at a different time point, the same way. It reduces the need for mover-stayer modeling because of that, since movers and stayers can be captured by different random intercept values. So instead of having the dichotomy of movers and stayers, you have a continuous difference between those who tend to move more versus tend to stay more by the F values differing across individuals. In Mplus terms, you have a model command for the random intercept factor F, which looks like this. F measured by, in this case, 2 indicators. And we free the loadings of those indicators so that we set the metric instead by fixing the factor variance to 1 and the factor mean to 0. That turns out to be the preferred metric setting. And those 2 loadings will be labeled P1 and P2. That's at lambda 1 and lambda 2. And we want to hold them equal across time. So we have the same labels for the second time point and for the third time point. And the semicolon doesn't come until down here. Now, RI-LTA typically needs more random starts than regular LTA. ML estimation, which we use here, requires numerical integration over this factor F. And numerical integration can in principle be time-consuming, but in this case, we have only one dimension of integration, namely one factor. So this is the combination, of a continuous latent variable and categorical observed variables, like you have in item response theory, where you also have to use numerical integration. So in the analysis command, we add algorithm equals integration, and the default number of integration points is 15 as usual, but in some cases you need more points, perhaps 30, to increase the numerical precision and thereby be able to replicate the best log likelihood. So you may add integration equals 30. Now on slide 34, I point out that there have been software improvements over the recent versions for both LTA, regular LTA, and RI-LTA. RI-LTA can be time-consuming, as I mentioned, due to numerical integration and needing many random starts to find the global maximum. So we made an improvement in version 8.4, which was released November 2019, getting significant speed improvements using a new 3-stage random start search and using some specialized computational algorithms. And this is described in the technical report here, random starting values and multi-stage optimization. And you can click on this and you get to the report. And a quote here is 20 hours computation in Mplus 8.3 can be done in 8.4 in less than 15 minutes by utilizing these advantages, as well as updated hardware using the i9 Intel CPU instead of the i7. In addition, we've made substantially simplified output for these mixture models with multiple latent class variables, both in version 8.4 and in version 8.5, and now further in version 8.6, which has been substantially improved in terms of output clarity and interpretational ease. Just looking at two examples then regarding speed. Here's an example for continuous RI-LTA model, so random intercept factor, 3 latent classes, 5 categories each, 12 observed categorical variables, 1-dimensional numerical integration, 3,000 people, moderate to large start set. That's example 4 on my computer, which was and is actually an i7 with proc processor equal to 8, took 14.5 minutes. On a colleague in the Mplus group computer, it took 8 minutes, same number of processors, but with the i9 Intel CPU. And then you increasing the number of processors which are available for that configuration, you cut it down to 7 minutes. So a factor of 2 from 14 minutes down to a little over 7 minutes. And example 5, there we see the example where it took almost half an hour before, and now you can get away with doing it in less than 15 minutes. But that's a heavy example. Now regarding the numerical imprecision and the negative, we have this concept of negative apps changes in the log likelihood. You know, you want over the iterations that the log likelihood should improve. So not have negative apps changes, which are in this second column, and this is your screen printout. So the second column, you see that you have some negative values here coming up in several places, and that can make the computations more difficult, take a longer time, and can make it harder to replicate the best log likelihood. And it usually points to the need for using more integration points to get a log likelihood computation that is such that it always improves the log likelihood, so no negative apps changes. Absolute value changes is what it refers to. Now, better numerical precision avoids these, but leads to slower calculations. So that's once again going from 15 to 30 integration points, which usually clears this up. But note that negative apps changes may appear only for the poor solutions, those with worse log likelihood values than the optimal solutions. So that's of less concern. But you don't want to have these negative apps changes present for the best log likelihood solution. You can also try to avoid these negative apps changes by switching off the adaptive integration setting that's default, which then forces monotonic log likelihood improvement. So forces you to not have negative apps changes, but you do lose some precision in the computations. Now, another practical matter is what kind of sample size and what kind of number of time points do you need for these analyses with RI-LTA? Well, in general, with categorical latent class indicators, large samples are recommended also for regular LTA and certainly for RI-LTA. N should be in the order of a couple of thousands, preferably. Reading data has 3,500 observations. Now, with binary indicators, regular LTA, when it is the correct model, may be all right already at 500 observations, but your power will be low for finding effects on transitions. So if you have covariates and try to find effect of covariates on the transitions, you may not have enough power to reject that the covariate influence is 0. RI-LTA performs well when you have at least 3 time points, as long as you have at least 500 observations. Now, with binary indicators and 2 time points only, you may need at least 4,000 observations, as indicated by a simulation that I did in the RI-LTA paper. With binary indicators and 500 observations and 2 time points, and if the RI-LTA is the true model, even though that's not the optimal setting for RI-LTA, that is too few observations, too few time points, RI-LTA does have less bias than regular LTA. So if the data were truly generated by an RI-LTA model, there's no comfort in using regular LTA, which in principle could be good at low sample size and only 2 time points. RI-LTA has less bias and is preferred. Now, with continuous indicators, the situation is quite different. Then with 500 observations and only 2 time points, RI-LTA gets good results. So there you have a first quick overview of advantages and practical considerations for using RI-LTA. So next we'll go to some outputs and take a look at RI-LTA in practice on the reading data. Segment number 7 ended on slide 38, where we were ready to go to outputs 3 and 4 for the random intercept LTA runs. Here is the setup for that RI-LTA run. We take a look at the input instructions and see what's different from before. Well, now we're going to talk about algorithm equals integration here to be able to bring in a factor, a random intercept factor. So we have this situation where we have a continuous latent variable and we have categorical observed variables, and with maximum likelihood estimation that leads to the need for numerical integration. And the default is 15. If you start seeing negative chain improvements in the log likelihood over the iterations, then you may have to change it to integration equals 30. But here, since we commented that out, the default of 15 is in operation. The model statement then adds only one segment here. We measure a factor f by the 5 latent class indicators at time 1, 2, 3, and 4. And we avoid the Mplus default metric setting of fixing the first loading to 1 by having this asterisk that frees them all. And we instead set the metric by choosing factor variance 1 and factor mean 0. And the loadings are held equal across the different time points, P1 to P5, or the 5 loadings for the 5 items at each of the 5 time points, held equal. And that's the only thing that you have to do. And then you're off and running. So let's take a look now at the model warnings and errors. So here we have the list of log likelihood values from our random starts. And we see that they are very much the same, all of them, except they differ in the last decimal here for some of them. But Mplus considers this to be a true replication. Actually, the tolerance is 1 here, so only if it went to 329 or 327, then you would consider it not replicated. Again, we're going to keep an eye on the best opseed here, opseed for the best run, in case we don't like the class reordering. We have the common issue of one or more multinomial logic parameters fixed to avoid singularity of the information matrix. And here there are a few more than for the regular LTA, and I will return to that in a second. What we really want to take a look at is the latent class indicator means and probabilities for each latent class as a first step, to see that we have the classes in the order that we like. And you see here then that this seems to be the medium class, class number 2, and this seems to be class number 3 with high probabilities all the way to the more advanced items, and the third one seems to be class number 1, where the probabilities are lower than for the other two classes. So the classes appear in the order 2, 3, 1. So we want to reorder that into having the third one first, so 3, and then 1, and then 2. So we want to do it as 3, 1, 2 in the second run. So let's take a look at that. And that is the reordered run for RI-LTA. And the only change then is that we, instead of starts, we use the opseed that we found in the first run, and we use this reordering 3, 1, 2 for all classes. Now you can go to the model fit information, and we're going to compare this to regular LTA in a little bit. And first verify that the order is the right one. So you have class number 1 with low probabilities here for the bottom 3 items, class number 2 which has a little higher probabilities, and class number 3 which has the highest set of probabilities. So we're able to get that in the right order as we wanted. And we should also check that we have the same log likelihood value as we got in the first run. And Mplus does that automatically, but you may want to check that also. Now, in this case, we get some information of interest that's from the model results, because we already have something in our naturals in a scale that we're used to. We don't have this problem of having to translate to probabilities or odds ratios. And that's the new thing, the factor measured by the different items at the different time points. So you see here they have factor loadings that repeat over the time points. 3.5 comes back here for each new time point. So we have time invariant factor loadings, as is the idea of random intercept factor addition to the LTA. And we see that they're all positive and all significant. And we interpret the factor as a factor that, when it has high values, makes you do better on these items. And some would interpret that as a trait, an individual differences concept, so that some kids are more able to solve these problems than others. Or you can see it as taking out the differences between people, so that you can study the differences across time for people in the latent class transitions. Now you can also see this in terms of IRT parameterization. So if you're into item response theory, this is really a item response theory model, and we translate then our loadings and thresholds into item discrimination and difficulty. And the item discrimination here is the same as the loading, because the factor variance is fixed at 1, whereas the difficulty is the threshold divided by the loading, so they come out this way. So if you prefer that, that's another way of looking at it. Now, 2 technical comments before we take a look at the comparison with the regular LTA. One is this message that we got. We have 1, 2, 3, 4, 5 parameters that got fixed. And that corresponds to what we see in the latent transition table here, or tables. We have 1, 2, 3 exact zeros, 4, and 5. And those are the causes of the fixed C on C slopes. Again, it's totally innocuous, and you can trace them back to these zeros. The fact that no child unlearns or goes back in their development. Now, you will see then that it's actually it refers to C2 number 1 and C1 number 1 and C2 number 2 and C1 number 2. So these two, instead of where the zeros are, and that's a trivial technical matter, where that the lowest row here is where the intercept parameters are estimated, and they are listed in the computer, in the program. They are appearing before the slopes appear. So not until you get to the slopes do you get this indication of needing to fix them, otherwise the information matrix would get singular. So that's why you don't see them in the exact same spots, but you have the same number of them appearing here. That's one technical point, which means that this message can be ignored. It's explainable that way. Now, another thing you might want to take a look at is the Tech 8. So here you have the Tech 8. We did the reordering, so we have 2 of them actually, but we can look at only 1 of them. And we see here positive apps changes. We have no problems in monotonically improving the log likelihood, which is a good sign. Sometimes you don't get convergence when you have a lot of large negative apps changes. And again, these 2 end at the same log likelihood, the reordering as the initial run. Now we go back to model fit here, but let's also bring in a comparison, the regular LTA reordered. So we have that, and we can use this feature of tiling things vertically, so you have them side by side. So on the left you have the regular LTA, and on the right you have the RI-LTA. RI-LTA has 5 more parameters because you have 5 loadings that are held equal. So that's why. And you see that the likelihood is considerably higher. This is less negative than that is. And the BIC is considerably lower, that is better than this. And we're going to make a detailed comparison of the 2. You can see that the latent class probabilities are also quite different, and you can see that the measurement probabilities are pretty similar, but the latent transition probabilities, that pattern, is quite different between the two. And we can take a look at the details of that and try to understand a little bit more about that. Now we'll turn to comparing the results between regular LTA and RI-LTA. And we'll also talk about how one decides on the number of classes, and further on checking model fit and model modifications. On slide 40, you see then a simple tabulation for regular LTA and RI-LTA, number of parameters, log likelihood, and BIC. And we see that RI-LTA has 5 more parameters than regular LTA. That corresponds to the 5 factor loadings for the random intercept factor that we hold equal across time. So 1 for each of the 5 latent class indicators. And you notice then what a big improvement we get in the log likelihood. Minus 20,000 is far higher than minus 21,000. It's about 1,500 points better. And in terms of BIC, it's also a big improvement. BIC being lower means it's better. That is, weighing the likelihood together with the number of parameters to get a BIC value. It's easy to get a better likelihood by just increasing the number of parameters. So we have a penalty in the BIC computations, which prevents you from simply increasing the number of parameters. The log likelihood ratio chi-square difference testing that we typically do, 2 times the likelihood difference is chi-square distributed with the difference in number of parameters. That's not quite right here because the two models differ with respect to a factor, so a random effect, so you have a variance of a factor involved here. So saying that that factor doesn't exist, which we say for regular LTA, means that we are testing on the border of the parameter space, which renders the chi-square distribution assumptions invalid. So it's not exactly chi-square distributed. It's probably not far from it, and actually it would be interesting to do a Monte Carlo simulation study to see how close or how far away it is from a chi-square distribution. Now I would say that it's not needed to get into chi-square difference testing because we have such large differences in the log likelihood and in the BIC. And in fact we can stay with BIC as the only gauge of model quality, relative model quality. It's clear that this value is so much better than the value up here, and sometimes though we want to keep track of the log likelihood to see if it improves or not. That also relates to model identification issues. Now BIC is good because it can be used even for non-nested models or for models that are nested but still have this problem of testing on the border of the parameter space, the zero variance issue, as long as you have the same dependent variables. And that's the case here. You have the same 20 binary latent class indicators. So let's take a look at the estimates then from the two models and see how they differ. So first we start with the measurement probabilities for the 3 classes, regular LTA and RI-LTA. And we have the 5 binary latent class indicators here. And we remember this pattern from segment 2, going through the example. We find that the beginning item is indicative of being in at least class 2. It's not a high probability in class 1. Similarly, ending is indicative of having reached class 2. And site is indicative of having reached class 3 proficiency. On the right, you see a fairly similar pattern. That is, we get a strong increase in the probability going from class 1 to class 2 for the beginning item. Not as clean as over here, There's a probability 0.3 here, whereas 0.07 here. And for the ending item, there you have more similarity, although you have a little bit higher probability for class 1 here. So less discrimination. Same thing for the site item. Similar pattern, but a little higher probability of being class 2. So less discrimination between class 2 and class 3 in RI-LTA than for regular LTA. And that may be a pattern that we will see more often. It is actually a function of how we specify the model with a random intercept factor. I described that in the psychological methods paper when I talk about the measurement model. However, you can see it as a more correct representation of the discriminatory power of the items, because the RI-LTA model fits the data so much better, as we saw. Slide 42 then talks about the latent class probabilities at the different time points. So each of the 4 time points here, and here are the 3 classes, and we have regular LTA at the top and RI-LTA at the bottom. So starting in the fall of kindergarten, regular LTA says that we have about 69% in the lowest class, whereas RI-LTA says that we have about 95% in the 0 class. So quite a big difference here. And you may ask then, well, which one is correct? Well, RI-LTA fits better, so that would tend to make us believe that this number is more reliable. But we will take a closer look at the fall time point and see if that holds up, that RI-LTA fits better in that part of the model. Likewise, if you go to the end, regular LTA says that 81% have reached the highest proficiency class 3 at the end of first grade in the spring, whereas RI-LTA says it's 97%, so quite a bit higher there as well. So there are clear differences here in the interpretation of the data, and one can argue that regular LTA, if it fits much worse, shouldn't be trusted. Slide 43. Here we take a look at the key issue of transition probabilities. You have at the top here you have regular LTA, and at the bottom RI-LTA. On the top left you have the transition from the first to the second time point, fall of kindergarten to spring of kindergarten, and on the right you have the transition from fall of first grade to spring of first grade. So I'm showing you 2 of the 3 transitions. What I left out is the transition from spring kindergarten to fall first grade. So regular LTA says that for those who start in the lowest class in fall of kindergarten, 34%, there's a 34% chance of staying in that low class versus a 65% chance of moving on, which would be a better outcome. If you go down to RI-LTA, it says that you have a much lower chance of staying in class 1 if you start there, and a higher chance of moving on to class 2. So those who start in lowest class of fall kindergarten have an 82% chance of moving on to class 2, which is quite a lot more optimistic of a result than for regular LTA. You can also look at the transition from fall first to spring first, and for instance you could take a look at, for those who were in class 2 in the beginning of first grade, probability of staying is 13%, of moving on to class 3 is 86%, whereas again RI-LTA has a more positive view, smaller chance of staying in the same middle class, and a higher chance of moving on to the better third class. So different interpretations. Going to slide 44, we get back to the issue of typical transition paths that I talked about in segment 2 for going through the example before we got into all the methodologies. So here are the estimated frequencies for the 3 most frequent paths through the latent class variables over the 4 time points. So this row is then the most frequent path. 33% of the individuals follow that path. That is the path of starting in the lowest class in the fall of kindergarten, going on to the higher class 2 spring, staying there over the summer, and then going to class 3. 33% follow that path. Whereas for RI-LTA, you have rather 71% following that path. And going to the more beneficial path, starting already in class 2 and going to class 3 already in spring of kindergarten and staying there, that was 10% for regular LTA, whereas we don't even have that path among the 3 most likely, so it's less than 5%. So clear differences. And again, just to remind you that this kind of information is shown in Tech 15 under the heading Final Class Counts and the proportions for the latent classes based on the estimated model. Turning to slide 45, we should discuss the key issue of deciding of the number of classes. We're going to use BIC here, and we're going to talk about 2 approaches: 1 time point at a time, or analyzing all time points jointly. And this is, again, we're talking about analysis without covariates. So here you have the number of classes, 2 to 5. And commonly for regular LTA, you start with an LCA, a latent class analysis, for each of the 4 time points. And here this is shown, the BIC values are shown for 2, 3, and 4 classes. And you see that the bolded value here is the lowest, that is the best for all 4 time points. That is, this would indicate work with 3 classes, which is also substantively motivated, as we have discussed the 3 stages of reading proficiency acquirement. Now you can also analyze all time points jointly and vary the number of classes. And you see then that BIC keeps going down, and it does not show a minimum like it did here, where it dipped down and then went back up. In every case it dipped down and went back up. That's what you want to see to be safely guided by BIC. Here that doesn't happen. And that could be an indication that you are not hitting on the exactly correct model. Some modification of the model may be needed for this minimum of BIC to show up. If you continue with 6 here, you might see, yes, another drop in BIC. And I think I found that, and not an increase. So no minimum seen. RI-LTA, all time points jointly, says the same thing. That is, you don't find a minimum, so there too there may be room for improving the model. Now for RI-LTA I didn't show the separate time point LCAs because, unlike regular LTA, a model for 1 time point at a time is not a subset of the RI-LTA model. For instance, if you do a latent class analysis plus 1 factor, like a factor mixture model, that's not a subset of the full model because it doesn't capture the time invariance of the factor loadings. So it's really a different model. So with RI-LTA, you would have to go with joint time point decisions. And we will see what the reason might be for this lack of a clear BIC decision on the number of classes. and this last bullet we already covered. See Tech 10 for model modifications or model misfit, then try a more flexible or an alternative model. On slide 46, we'll take a closer look at model fit and model modifications. In this segment, we're going to discuss checking response pattern fit and bivariate fit, and measurement invariance across time. Slide 47 then talks about frequency table test of model fit. So we have 5 latent class indicators at 4 time points. So we have 20 binary variables, and one can imagine then a big frequency table where all of those variables are crossed and looking at the frequencies of those cells. So that's a standard frequency table test where we use Pearson and likelihood ratio chi-square. So summing over the cells of the table, J sums over the cells of the table, you have the observed frequency and the model estimated frequency, square of that divided by the estimated. When you take a likelihood ratio approach, you instead look at the observed and the log of the observed divided by the expected. When all assumptions are fulfilled, these two tests tend to be very similar. They converge for a large sample to the same values. But in smaller samples, they can deviate quite a lot, particularly in cases where there are many variables, like there are with LTA. Many variables gives rise to too many frequency table cells, and even with a large sample you would have many cells having estimated frequencies close to 0. And when you have small estimated frequencies here in the denominator, the chi-square contributions from each cell tend to blow up and render the test not chi-square distributed, not usable. And in those cases we simply write the chi-square test cannot be computed because it's too large, that is, too many 0 or small frequency cells as estimated. You know, we have 5 binary indicators of 4 time points, which is 2 to the power of 20 over 1,000,000 cells. So obviously, even with a huge sample size, you don't cover all of those cells with observations. Actually, only 604 cells have observations. 604 times 5 per cell would be about 3,000. Therefore, one could imagine that our sample size of 3,500 individuals would be enough, but only if they spread out evenly across the cells, which they don't. So you fall into this problem of estimated frequencies close to 0, and we have to give up on that frequency table test. But there are alternative checks. You can look at how the most frequent response patterns, how well they are fit, and even though you can't do a big table, you can reduce it down to a bivariate table or a set of bivariate tables where you can check the fit. And this information is provided in Tech 10. So here's what it looks like in Tech 10. Looking at the response pattern fit first. Most frequent response patterns and chi-square contributions is something that we've added in version 8.6, where we list the 10 most frequent response patterns and their fit, which is helpful when you have 604 to go through. Here is just the 10 most frequent. And we find then that the response pattern 201 has a particularly large discrepancy between the observed and the estimated frequency, and therefore gets a large log likelihood contribution to the frequency table, measured by log likelihood or measured by Pearson. The chi-square contributions are very large. Standardized z-score is also very large. That pattern is actually, if you look at the bottom here, is the pattern of all zeros for all items at all time points. So a child that is in the lowest class at all time points, certainly. A child that does not even solve the letter recognition item. If you then compare the regular LTA versus the RI-LTA, you see that the observed 91 is better fit by RI-LTA as 30.84 versus 5.74, and therefore the chi-square misfit contribution is 187 instead of 502. Still not a good fit here. It sort of calls for adding some special model feature that picks up the all zero individuals, which could be done by a separate class perhaps. So one can experiment with model extensions here. Now there are other cases also to look at. For instance, pattern 61 is getting a high value. Pattern 61 is again better fit with the RI-LTA model. Now the bivariate fit in Tech 10 is useful to look at as well. And here in this table we're looking at the first time point. So we're looking at first time point has 5 items, so we have pairs of items, letter recognition at time point 1 paired with beginning at time point 1, paired with letter recognition paired with ending, and paired with sight paired with words in context. So the 5 items, so 5 times 4 is 20, so there are 10 pairs here that we're looking at for the first time point. And the reason I'm focusing on the first time point is because we have found that discrepancy in the class percentages between regular LTA and RI-LTA. And even though RI-LTA fits so much better overall, we want to make sure that it also fits better in important parts of the model, time point 1 in this case. So here's an example how you read this. The pair of letter recognition and begin at time point 1, you have a bivariate log likelihood chi-square at 27, so that's what we're recording here for regular LTA fall of kindergarten. So if you look at these, compare these two columns, regular with RI-LTA, you see that RI-LTA gets a smaller chi-square contribution than regular LTA in all cases down here. So it fits better. I should mention that this chi-square is for a 2x2 table, and we don't really know what the degrees of freedom is, because model has this part, the bivariate part, shares parameters with many other parts in the model. So it doesn't have a specific number of parameters pertaining only to it. So we don't know what chi-square is, or what the degrees of freedom is. And we use this chi-square more as a descriptive measure of fit. We also give a standardized residual that I will show you later on. But as a descriptive measure, we see that second column here has lower, that is better values, better fit than the first column. So at time point 1, we would trust RI-LTA better. Now if you go to the last time point 4, you have the same comparison. Here actually regular LTA is better for the pair of letter recognition and beginning than RI-LTA. In other cases, regular LTA is worse. Here regular LTA is better. Here it's worse, same, better, worse, 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 worse. So to find this, so overall I would say that time point 1 RI-LTA clearly beats regular LTA. Time point, the last time point 4, maybe not so much, not so pronounced, and maybe that reflects the fact that we can improve both models at time point 4. At time point 4 then being influenced not only by the class variable at the first time point, but by all latent class variables and the specification of the transitions over time. And maybe there's something we're missing in the transition modeling. So let's go to output 2 for Webtalk 2 and I will do it by going this way. Here you have the regular LTA reordered, the second run. And here now we find technical 10 output. And we have different subsections, all the response patterns, all the 604 response patterns, and listed, you know, zeros and ones. And then the frequencies for those response patterns and the chi-square contributions. And then the most frequent response patterns, like I mentioned, 20 most. And then univariate fit and bivariate model fit. So let's take a look at the most frequent response patterns first. Here you have then the display which shows pattern 201 and it misfit that the regular LTA finds for the children who score 0 on all variables at all time points. Below that you have the univariate model fit information, and then further down you come to the bivariate model fit information. You then see that here we recognize the 27 that I showed you before in the table between letter recognition 1 and begin 1. Let's take a look at letter recognition 1 and ending 1. That's a high chi-square contribution, that is a poor fit for this bivariate table. You have an H1 and H0 column. H1 is the observed frequencies in that table divided by sample size. And we see a particularly large contribution here. The chi-square is overall, but you can look at the z-score, which is for each of the 4 cells, and you see that's particularly this cell, when both are in category 2, getting that item right, that discrepancy between 0.175 and 0.213 seems to be significant, because that is a z-score, and therefore contributes to the bivariate log likelihood chi-square. So there's something not quite right in the relationship between letter recognition 1 and ending 1 for the regular LTA model. Now going back to slide 49, here we have discussed this bivariate table for time point 1, or these bivariate tables rather for time point 1. Let's now turn to looking at the appropriateness of this default assumption of measurement invariance across time. So we are focusing on this part of the model. We're not touching this part up here. We want that to be a random intercept factor definition of equal loadings across time. But here, the measurement of the latent classes, we want to test to which extent that seems reasonable. 2 approaches, one problematic and one much better. Problematic is when you let all indicators be invariant across all time points versus no such invariance. So none of them are invariant. A regular LTA gets a chi-square for that difference, which is hugely significant. RI-LTA as well. So it's strong rejection of measurement invariance across time, but two problems. No information about which indicators contribute the most, at least not directly. No direct information. And more importantly, the class sizes and the interpretation of the classes change when you don't hold the measurement part of the model invariant across time. I think it's better to allow for non-invariance for one indicator at a time across all time points for each class. So one at a time, that then, if you have enough indicators at least, tends to hold nail down the latent class interpretation okay, and hopefully the latent class sizes as well, largely at least. So you can go through one indicator at a time to do this. And you can speed it up by, for the fully invariant run, you can request S values. That is, you get the ending values and can use them as starting values for a new run, where you use starts equals 0 because you're so close to the best solution. You don't need to have many random starts. And you free up only one item at a time. So doing that, here's the result, one indicator at a time. This is chi-square difference testing with 9 degrees of freedom, so this is appropriate chi-square difference testing. So we have regular LTA and RI-LTA for each of the 5 items here. And you see then that the site item and the ending items are the big offenders to measurement invariance. The site item more so than the ending item. And site item again is sight words, commonly used words that young children are encouraged to memorize as a whole by sight so that they can automatically recognize these words in print. So once you found that, you can of course free that item and let that be non-invariant, and then redo this analysis because these values here may change for the other items once you have allowed that one to be free, to be unequal across time. Slide 52 shows you how you do that. So you have the model for the first time point. You have the usual three classes rather here that we label those thresholds differently. They vary across classes. And then for the second time point, we repeat this statement up there, but then we modify it by freeing one of the thresholds. So putting that after the equality overrides the previous statement, that is statement of full equality. So it only holds the other items equal across time point, not the site item. Same thing for class 2 and for class 3. And then you do the same thing for site 3 in model C3 and site 4 in model C4. Turning to slide 53, we're going to take a look at adding residual correlations over time for the latent class indicators. And this draws on the techniques described in the 2015 paper by Tiemer and I in structural equation modeling. So this is applicable to both LCA and LTA. And the idea is that each indicator is allowed to have a residual correlation across time, and by allowing that in LTA, you are in effect able to perhaps find a big minimum for a given number of classes that you would otherwise not find. So for regular LTA, no covariates. We have the run that we talked about before, where we have no residual correlations. And now we're going to add residual correlations. And we're going to have 50 parameters. And the log likelihood is increasing rather, quite a lot. And so is BIC. BIC is considerably lower or better than without the residual correlations. 50 parameters come about because for each item you allow correlation for adjacent time points. So with 4 time points you have 3 adjacent correlations between adjacent time points, and 5 items is 3 times 5 is 15, which is exactly the difference between 50 and 35 parameters here. Now for RI-LTA with numerical integration, residual correlations are not yet available, but one can also argue that it's not needed. As you see, even without residual correlations, we have a considerably better BIC and considerably higher log likelihood. If you think about it, the RI-LTA also allows correlations between the residuals across time. For each item, it's actually lambda times lambda, lambda squared. If that is the correlation that goes via the random intercept factor. So those correlations, however, are held equal across all the 3 time points, across all the 3 adjacent time points, I should say. Whereas with the residual correlations that we used for regular LTA, those 3 are different. But with the interpretation of the random intercept factor as a constant trait, individual differences that are constant over time, we hold those 3 residual correlations equal across time. So in that sense, we don't really need residual covariances. That little difference between them being unequal versus equal is too small to bother with. Now, here's how you set it up in Mplus. It's still type equals mixture, but now we have the parameterization rescov. So you have the regular model, regression of the C on C, and then you add, for the first item, letter recognition is correlated between time point 1 and time point 2, and time point 2 and 3, and 3 and 4. So those are the 3 extra correlations or associations for item number 1. And then you do that for all 5 items. And that's it. So that's an easy way to check it out. This is also possible, of course, with continuous outcomes, where you just use no special parameterization, but just use the with statements. Another way to modify the model is to change away from the lag 1 modeling, which is the standard in LTA. So here we have a picture of 3 time points, and we can then entertain the notion that maybe we have lag 2 relationships going on here. That is, C1 influences C3 directly. And with the 4th time point, you would have C2 influencing C4 directly. This is easily done. All you have to do is say what's in the heading here, C3 on C1. And with our 4 time points, we would say C4 on C2 as well. Which means that you can also have C4 on C1 and have a lag 3 included. And this may be what this model that we looked at before make it not fit the data as well as we want to. That is, perhaps we've left out important lag 2 and lag 3 modeling. So let's take a look at slide 55 where we test this out. So first you have regular LTA and then RI-LTA. So the lag 1 model that we talked about, that we used so far, is this, becoming familiar numbers now. With lag 2, we add a number of parameters for the C3 on C1 and C4 on C2. And we see that the log likelihood goes up considerably, and the BIC goes down to some extent, to a large extent. And if you take a log likelihood ratio test, chi-square test of the difference, 2 times this difference, testing model 1 versus 2, the chi-square becomes 276 with 8 degrees of freedom, which is the difference here. So it's clearly significant, which meaning that you would choose model 2, the one that's bolded here. Model 2 with lag 2 is preferable. Here we don't show the investigation of lag 3, but lag 2 seems to be needed. For RI-LTA, the corresponding numbers are here. We get an improvement of the log likelihood with some, to some extent, but to a lesser extent than for regular LTA. The difference, testing 3 versus 4, gets a chi-squared value of 20 with 8 degrees of freedom, which really isn't that bad of a fit for this overall large sample size. And in fact, if you look at BIC, it is preferable for the simpler lag1 model, even though the chi-square test would tend to lead you to model 4. So I conclude that lag2 modeling is needed for both regular LTA and RI-LTA, but there's a much stronger need for lag2 with the regular LTA. So once again, including that random intercept factor allows a correlation more directly between the time points 3 and 1 and 4 and 2. And so the RI-LTA picks up some of that. Now you may ask them, what does the lag2 effects, what do they look like? And that you get out of Tech 15. We're going to take a look at how we investigate that in a second. And then you may ask, does lag2 modeling result in different decisions on the number of classes? So that's something for you to investigate if you are interested. And what about lag3? Does that lead to a different decision on the number of classes? So here then is how you would express these lag2 effects in probability terms, where you combine different results that you find in Tech 15. So what I'm going to show you, you have to compute yourself, say by Excel, but the building blocks are obtained in Tech 15. So let's think about the effect of C1 on C3. And we're going to think of that as marginalizing over C2, the intermediate latent class variable. Because Tech 15 gives you if the probability of C3 given C2 and C1, but now we want only the effect of C3 given C1, that direct effect. So the probability of C3 being in a certain class, conditional on C1 being in a certain class, is a sum of 3 sums of products. First we have probability C3 equals A, C1 equals B, for C2 equals 1, and then for C2 equals 2, and then for C2 equals 3, times the probability that C2 is equal to 1, 2, or 3, given the C1 B value that we want to consider. So we get this conditional effect out of Tech 15, C3 given both previous latent class variables, C1 and C2, and C2 given its predecessor. So this sum of products is what you have to evaluate outside of Mplus. But that would give you the direct effect, so to speak, the probability of C3 in a certain class given that C1 is in a certain class. Which could be interesting, you know, the starting point, how does it affect, say, C3 or C4 in another setting. Now note that in lag1 models, you know, we're talking about how to express lag2 effects, C1 to C3, but in lag1 models, this may also be of interest, for the reason that probability of C3 equals a certain class, given that C1 is in a certain class and C2 is in a certain class, that does not depend on B, doesn't depend on C1 being B. Probability of C3 is only a function of C2 in a lag1 model. We don't care about what happened before C2. There's no direct effect from C2 to C3. But if we want to calculate the probability of C3 equals A and C1 equals B, like up here, in a lag1 model, it's not independent of B. That is, the starting point does affect the probability of C3 equals A, as we saw already in the introductory example in segment 2. That is, this kind of a table that I've shown up here could be useful for you to compute in lag1 models as well, because they answer the question, how does the starting point affect the ending point. Looking at the outline on slide 57, we now turn to covariates added to the model. With covariate effects on the transition probabilities. We're going to start with the regular LTA and then turn to RI-LTA and compare the results. Here is a model diagram for 3 time points with an x variable that is added. And I think it's important to distinguish between 3 types of models. The first one being C1 regressed on x. So x has an influence only on the starting point of the process and only an indirect effect therefore on C2 and C3. This model really, as it's drawn, corresponds to the second type, C1 to C3 regressed on x. And I'm going to call that the main effect model and contrast that with an interaction model that we're going to take a look at in detail. And it's actually the model that's shown in the user's guide for Mplus in example 8.14. But I don't think one should jump straight to that model, but instead first look at these 2 models and then compare all of them using likelihood ratio chi-square difference testing before the interpretations start. So looking at C1 on x, so that's covariate influencing the starting point. I think it's a good model to use as a baseline model. You include x, but you don't necessarily include all the effects that x could have. So C on x is then a multinomial logistic regression because C1 is nominal. And as usual, the last class is the reference class. So the probability that C1 is in a certain class R, lowercase r, is the exponent of the intercept plus slope times x for category R divided by those exponents for all of the different classes, where the last one is 1 due to a and b both being 0 and e to the power of 0 being 1. The slope here is then significant because e to the power of that slope represents the ratio of odds, an odds ratio. It's the ratio of the odds of being in class 1 given x relative to being in class R, the last class, for a certain x value divided by the same odds, the same ratio, for another x value minus 1. So you have a 1 unit change. For instance, x equals 1 versus x equals 0 for a binary x like poverty. So you have this odds for x equals 1 divided by the odds for x equals 0, and that ratio of odds becomes an odds ratio. Here I just restate those 2 bullets and look at the output that we get from Mplus, where you have under categorical latent variables a regression of C on poverty, and there are 2 such slopes. Those are the B coefficients because the last B is 0. And we give the point estimate, this loaded value, and its standard error, but then we don't give the ratio of estimate standard error because that would imply that we accept using a symmetric confidence interval. Instead, we're going to use a non-symmetric confidence interval that we described how to compute in the technical part. Here is the confidence interval, and since that interval does not include 1, we can say that the odds ratio estimate 8.1 is significant. Likewise, we have class 2 influenced by poverty. That odds ratio, yes, is a 1.88, whereas that one is not significant because it spans 1. The confidence interval spans 1. And you find these results in the output under the heading Logistic Regression Odds Ratio Results. Now looking at the main effect model, the second model, you have then x influencing all 3 latent class variables. specified simply as C1 to C3 on X and C2 on C1 and C3 on C2. Number 3, the more complex model, is the interaction model, which you recognize from Users Guide 8.14. So here you have then the influence from X on C2, that is C2 regressed on X, is C1 specific. You have this broken arrow showing that C1 influences this slope. That is, you have an interaction between X and C1. Same thing, the regression of C3 on X varies, that slope varies across the C2 classes. So we're saying we have a C1 specific C2 on X and a C2 specific C3 on X. So that's the more complex model, which you don't always need. Here's what it looks like in Mplus Logit formulation. Main effect model and interaction model, C1 and C2. And we have this Logit table that we show in the user's guide at the end of chapter 14. Here with the addition of influence from X. In the main effect model, the influence of X on the C2 variable is the same irrespective of the starting class for in both cases. The effect varies depending on the C2 class, class 1, G1, class 2, G2. In the interaction model, however, C1 specific C2 on X, then the G slopes vary across the C1 classes. So the effect on C2 depends on where you started. Same thing for C2 class 2. Those effects vary. And in all cases, we compare to the last class as the default in Mplus. Now, turning then to odds ratios for the transitions, we note then, as in the technical part, that each row represents a regression with a nominal dependent variable. You have 3 categories here for C2. Mplus modeling using the last class as the reference class. So let's take a look at how you would interpret G21 here, that slope. So we look at row 1 and that expression A2 plus B21 plus G21x. It's the log of the odds of probability of C2 being in class 2 given the first row and x relative to C2 being in class 3, the last class, for that row and x. Now we're going to consider the ratio of this odds for x equals 1 and x equals 0 corresponding to poverty. The log of this odds ratio is G21, because when you compare x equals 1 with x equals 0, the A2 plus B21 terms cancel out. That is, when x equals 0, this term doesn't exist. You have A2B21, and ratio of odds, log of a ratio is the log of 1 divided by the log of the other, so the A2 plus B21 term cancels out. But that's a lot of technical stuff. But that means that exponent of G21 is an odds ratio that describes the effect of x on the odds of being in C2 equals 2 versus C2 equals 3 for C1 equals 1. So in the main effect model, this odds ratio effect of x is the same for all rows, for all classes of C1, and the odds ratio is shown under the heading Logistic Regression Odds Ratio Results. Now, in many cases, you would want to compare to the last class. For instance, in the reading example where you have at the last 2 time points, that is fall and spring of grade 1, you want to look at the odds of compared to ending at the best class, class 3, at the end of spring. But in other cases, that's perhaps not best, most interpretable way of looking at things. So once again, we have this expression, and this is just repeating what I said on the previous page. C2 equals 2, C2 equals 3, for x equals 1. Same thing for x equals 0. That's the odds ratio. But instead of using the last class as reference, C2 equals 3 that is, transitions are often more easily understood by using the diagonal, that is the stayer class, as a reference, which for the first row would be C2 equals 1. And the diagonal here is what we're going to consider. So that's instead C2 equals 2 given C1 equals 1 divided by C2 equals 1 here instead of 3 up there in both the numerator and the denominator. So instead of using the last class as reference, transitions are often more easily understood by using the diagonal. And then you have a logit pattern like this, that is, you put the zeros on the diagonal instead of in the last column. And the reference class for each row, of course, has odds ratio 1, because both the numerator and denominator odds are 1. You divide in the numerator and the denominator is the same. So here's what it looks in a real example then. This is for model 3 and run 6 on slide 67. Run 6. Here we compare poverty equals 1 with poverty equals 0 for regular LTA with C1, C4 on poverty. So now we're going to take a look at the odds ratio, and you notice then the feature of 1s on the diagonal. So we're abandoning the Mplus default, and automatically Mplus does this reparameterization. And we can consider, for instance, this odds ratio and its 95% confidence interval, which does not include 1, so it's a significant odds ratio, 0.305. And the interpretation is the odds of transitioning to the second class, this class, relative to staying in the first class is 0.305 times lower. The odds is 0.305 times lower for POV equals 1 than for POV equals 0, and significantly so. So the odds ratio is 0.305. And here is the confidence interval taken from up here. So we're saying that the odds is 0.305 lower, the odds ratio is 0.305, significantly less than 1. And this is transitioning from C1 to C2. So the odds of transitioning to the second class, which you want to see between fall kindergarten and spring kindergarten, that odds is much lower for children from poverty households than for non-poverty households. So that makes substantive sense. So this is given automatically in the output under the heading Covariate effects on transition probability odds ratios. So that's a new feature in 8.6, which we felt we needed to add, given many questions about how to think about the effects of covariates on transition probabilities. And we're going to talk this through in more detail in outputs 5 and 7 for this Webtalk in the next segment. So in segment 12 we ended with this slide 67 and the suggestion that we go and look at the Mplus outputs for runs 5 through 7 to see how this plays out in practice. So we'll do that, and here is then the first run, which is bringing in poverty into the use variable list and does the regression of C1 on poverty as a baseline model. That's all we need to do with that run, just then also record the number of parameters, the log likelihood, and big. Now go into the main effect model, that's the run 6, we take a look at the input, and we simply have C1 through C4 on poverty. And here we might want to take a look at some of the results. The logistic regression odds ratios, for instance. We have then C1 on poverty, the two classes. The last class has coefficient 0. C2 on poverty, C3 on poverty, and C4 on poverty. And these are odds ratios, the effect of X on this latent class variable. And here we have the number 8.101, which is familiar from a previous slide, with the confidence interval here not including 1, and therefore indicating a significant value. We can also take a look at the transition probability odds. Here it is first evaluated the sample mean for all covariates. So in this case, the sample mean of poverty, so an average in between poverty and non-poverty. We get that for the 3 transitions. But more interesting, probably, is the covariate effect on transition probabilities, transition probability odds ratios rather, the effect of poverty. And here we take the tack of comparing to the diagonal class of stayers. So here you have the transition from C1 to C2, C2 to C3, C3 to C4. And here you have the value that we looked at before, 0.305, which is significantly less than 1, with the interpretation that we just talked about in segment 12. Now, turning to the interaction model, you have then run number 7, and this we got to pay a little attention to the input. Here we're going to have class-specific influence of poverty. So we regressed within model C1 and the different classes of C1, 1, 2, 3. We regress C2 on poverty, so making those slopes different. Same thing for model C2, C3 on poverty, different, and for model C3, C4 is different. Now, what you want to do then is to have C1 on poverty mentioned here only, not regress C2 and C4 on poverty, because that leads to a non-identified model where these regressions are both specific and overall, and that's a common mistake. So for that, you just then record the log likelihood, number of parameters, and the BIC, and we end up with a table like this. We first may want to run a model without a poverty covariate, which we have done before, and then do a baseline model, C1 on poverty, and this comparing model 2 and 1 establishes that poverty has some effect on the latent class variables. That's what we want to establish first of all. And we can do a likelihood ratio test, quite kosher test here. 2 times the log difference, 2 times the difference of the log likelihoods rather, is 310 with 2 degrees of freedom, the difference in the number of parameters, which means that we definitely should choose model 2 over model 1, which makes sense. And then we take a look at whether or not there are any effects on transitions that are significant. So we start with the main effect model, which was run number 6, where we regress all of these C1 through C4 on poverty. And we see then that the likelihood is better, and the BIC is better as well. Doing the chi-square difference test of model 2 versus model 3 shows a strongly significant effect. That is, you would need to have model 3, the bolded model here. And then we can turn to the interaction effect model that was in run number 7, where you have these class-specific effects, C1, C2, C3 class-specific effects on the next latent class variable. The log likelihood improves a little bit, 5 points here. But if you do a likelihood ratio test of model 3 versus model 4, model 4 here, you get a chi-square of 10 with 12 degrees of freedom, so that's not significant. And therefore you would choose model 3 here. And BIC also agrees with that. It's the best BIC is for model 3. So that's the main effect model. So that's the one you should interpret. You don't have to then get into all the details of the interaction effect model. I should mention in passing here also that throughout the chi-square difference testing, I take this simple approach of not using the MLR estimator scaling correction factors, because they are close to 1 and wouldn't make a difference, I think, in the choice of models here. But if you want to be more careful, you can do the scaling correction as described and do the chi-square difference testing as described at this part of our website. Finally, then, take a look at what difference it makes to bring in a covariate. We look at just class percentages here for this regular LTA analysis. No covariate, you have the classes 1, 2, 3 and the 4 time points, starting with 69% in the lowest class. But what happens to these class percentages when we add the poverty as a covariate in the main effect model 3? Well, they remain almost intact, no change at all, really. So in this case, and that's obviously clearly not always happening, but in this case, bringing in a covariate in this one-step analysis does not change the class formations at all here. Turning to slide 70, we will consider transition probabilities influenced by covariate for random intercept LTA. We have a picture here for 3 time points, and the new feature is an X variable, a covariate, that influences the latent class variables and also, and more importantly, the random intercept factor. X is a individual differences background variable, and therefore it should mainly influence the individual differences variable f here. However, for different groups like poverty, non-poverty, we can expect the latent class proportions to be different, and also the latent class transitions. So we want to investigate whether X has an influence going also this way. We're going to start with a look at the outputs for 2 models. These are outputs 8 and 9, and then we're going to go through a list of fit statistics, log likelihood, and BIC for a variety of models. Turning to output 8, let's take a look at the input instructions. We have the poverty covariate. We have the 4 latent class variables, and we're working with an op-seed here that comes from a previous run where we weren't happy with the order of the classes, so we reordered them using op-seed and S values. You see the S values command here at the bottom. Again, we have the random intercept factor measured by the 5 indicators at each of the 4 time points and equalities of those loadings, and the factor variance fixed at 1 and the factor mean at 0. Actually, this is then the residual variance of f and the intercept of f in the regression of f on poverty. So this is a new feature. We regress f on poverty, so the mean and variance of f is contributed by poverty. Here we have then the usual lag 1 transition relationships, and we have all of them regressed on poverty here. And you see the usual measurement model, specifications, invariant thresholds across time. So this is the main effect model, where we allow all of the 4 latent class variables to be regressed on poverty. Let's see then what happens in this run. First, let's take a look at the warnings and errors, and we see familiar ones that we've seen before. And many of these transition logits are fixed, corresponding to 0 transition probabilities. I'm not going to go through the details of this now, but there is a section at the end of this web talk where I'll go into the error messages in detail to see which ones are meaningful and which can be ignored and which one you should study. Instead, let's take a look at whether or not we got the class ordering correct using the latent class indicator means and probabilities. So it's probabilities in this case because we have binary variables. Category 2 is then you get the item right, so to speak, and that's the low class, low probabilities towards the more advanced items. Whereas this is the middle class, a little bit higher probabilities, and this is the high class with high probabilities throughout except at the last item. So we got that ordered in the way we want to. In this case, we can interpret the model results directly because we have a familiar F by situation here. It's true that the items are binary, so this is really an item response theory type of model. So, but we are familiar with how we interpret loadings, or if you want to look at them in the IRT metric, it would correspond to the discriminations, as we talked about earlier. All of them are significant and positive, implying that F is a factor corresponding to perhaps reading preparedness or overall reading skills. And here we have the central result, F regressed on poverty, negative and significant. Negative meaning that the reading skills are lower for those in poverty, which makes sense. And we see then that the effect is almost 1 standard deviation in the F scale if we take the total variance of F to be approximately 1, which you can get from Tech 4. Now, what you want to focus on here now are the covariate effects on transition probability odds ratios. So you get this heading, odds ratios effect on poverty. So we get this output for each X variable. In this case, there's only one. And for each transition, C1 to C2, C2 to C3, C3 to C4. And we get, for instance, the value 0.501 up here. So an odds ratio is the ratio of 2 odds. And what are the 2 odds? Well, it's the odds of moving from class 1 in fall of kindergarten to class 2 in spring of kindergarten. That odds is only half as big for those in poverty relative to those not in poverty. So 0.501 is the difference in the 2 odds. So the odds is much lower for those in poverty to move on to class 2. And it's significant because this confidence interval does not include 1. True, there are some bigger than 1 odds ratios, like this, which wouldn't make sense. It's the odds of moving from class 2 to class 3 during kindergarten being higher for those in poverty. But also it's not significant. So it's based on very small frequencies and therefore it can be ignored. Here you have another odds ratio, 0.209, so even bigger difference in the odds of moving on to, in this case, class 3 from class 1 during the first grade. Since we have an x variable, we can also take a look at the calculator here, which is in the Mplus drop-down menu. And we have two options: conditional probabilities for the latent class indicators. We're not interested in that right now. And the conditional probabilities and odds for the latent class variables. And that's what we want to take a look at. And here now we want to assign a value of 1 to this poverty covariate. To take a look at that, and we apply that, and shows up as 1 here instead of the default of mean. And then we push OK, and we get condition poverty equals 1 here for a bunch of conditional probabilities for the latent class variables. So let's take a look at, say, the last one from C4 to C3. So here's the first mentioning of C4. C4 given C4 equals 1, 2, and 3, given C3 values 1, 2, 3. So here we condition on all previous latent class variables, but C1 and C2 don't matter. In the lag1 model, C4 is only dependent on C3, not C1, C2. So here are the values: 0.288, 0.059, 0.653. This is for the first row in the transition table. This is the second row when C3 equals 2, and this is the last row when C3 equals 3. Now this gets repeated here. C4 equals 1 for C2 equals 2 values, as opposed to C2 equals 1, and you see then that is the same, so it's ignorable here. We know that they are the same for lag1 models. So that's one model. And then we can take a look at model output 9, which I have here behind. And the input instructions for that differ. Here we actually have a run with the without the reordering, but it doesn't matter. We're only interested in the log likelihood here. So 160, 40, moderate number of random starts. F by, same fashion as before, and F on poverty. And we have the transitions here between the latent classes, the lag1 specified model. And then we have the gist of this. We have C1 on poverty here. And note that we don't have C2 through C4 on poverty, because they are instead included as interactions below here. So for model C1, this is the interaction model. For model C1, we have C1 class-specific C2 on poverty regressions. For each of the three C1 classes, we have a different slope for C2 on poverty. Same for model C2. C2 specific C3 on poverty, and for model C3, C3 specific C4 on poverty. So that's the interaction model, and it converges. It has a little bit more difficulty, probably because of being a much more flexible model. In this case, we're going to see it's not needed. So here you have fewer replicates of the best log likelihood. But it comes to a solution that we can trust and include in our list of log likelihoods and BICs to decide on the model. So in the next segment, we're going to turn to a summary of all of the results here. In this segment, we'll take a look at the various kinds of models that you can entertain for RI-LTA with covariates. So on slide 71, we have 7 different models. The first one being, again, the model without covariate as a comparison. And then model 2, the model of key interest to us in RI-LTA, namely poverty influencing the random intercept factor f. So that adds one parameter, the slope of that regression, and we see a drastic improvement in the log likelihood with about 200 points here. Testing in model 1 versus model 2, we get a chi-square difference test with 402, the value of 402 with 1 degree of freedom, so strongly significant. And we would reject model 1 in favor of model 2. And the big value also speaks for model 2. And once again, we note that in the chi-square difference testing, we take the approximation of not using the scaling correction factors because they're close to 1. But you can do the scaling correction factors and get a chi-square that's more precise. Model 3, then we try to replace f with C1 to see if that is just as good to use. Well, that improves the log likelihood relative to the first one, and it is a significant improvement. Chi-square is 20 with 2 degrees of freedom, so you would choose model 1 over model 3. But the BIC is not as good. The log likelihood and the BIC are not as good as for model 2. For model 4, then, we have both C1 and F on poverty, and that gives us a slightly better log likelihood value than having F alone as in model 2. But that's a chi-square of 2 with 2 degrees of freedom, so that's not a significant improvement, and we might just as well stay with model 2, so we choose model 2, the bolded model here, in this set of 4 models. And note that none of these models imply that we have any effect of the covariate on the transitions. F and the starting point C1, that effect does not affect the transitions, just the level, so to speak. Now, when it comes to transition effects, we have the main effect and the interaction effect possibilities. Main effect model, we can have C2 through C4 on poverty and F on poverty, or C1 through C4 on poverty and F on poverty. If you compare model 5 to model 2, yes, we find model 5 to be the better one. We reject model 2 with a chi-square difference of 44 with 6 degrees of freedom. If we use this model, model 6, which corresponds to output 8 that we discussed in segment 14, you would also, if you compare that to model 5, you would still work with model 5 as the simpler model and has a better BIC as well. Now, interaction effect model output 9, where we have interaction between x and the latent class variable at the previous time point, you get an improvement of the log likelihood relative to, say, model 5. But it's an improvement that's not really significant. With 14 degrees of freedom, the chi-square difference is 16. So you would choose model 5 here as well. And model 5 is the one with the best BIC as well. So model 5 might be the model, although model 6 wouldn't be too bad to use as well. Both of them have good BIC values. And it's interesting that the best BIC with the regular LTA is so much worse, 43,500 instead of the 40,000 that we're at with the RI-LTA. We can also check the class percentages, no covariate, and adding the poverty covariate. And for the 3 classes and the 4 time points, we find that the results are very similar. 95.50 versus 94.51 for the fall, and all the way to the last time point, 1,297 to 296. So the class formation doesn't seem to change very much by adding a covariate. No need for a 3-step analysis. Same thing was found for regular LTA at the top here as for the RI-LTA that we just looked at. But still, we note how different the class percentages are between regular LTA, be it with or without covariate, 69 versus 95, 94, 81 versus 97, 96. Here's an interesting slide, 74, transition probabilities obtained from the LTA calculator. Here's the case for regular LTA first, and then we're going to take a look at the RI-LTA. So this is model 3, run 6 that we talked about earlier. So you consider poverty equals 1, poverty equals 0, and the transitioning is from C3 to C4, that is from fall of first to spring of first. So the last 2 time points. So here we have the transition probability matrix for poverty equals 1 and the more fortunate group of poverty equals 0. So take a look, for instance, at this row starting in class 2 of fall of first grade. We have the probability of staying there 0.226 versus going on 0.764 for the poverty group. And for the non-poverty, the more fortunate group, you have a smaller probability of staying in that class 2 and a higher probability of going on to class 3, as would be expected. Now you could of course test differences in probabilities here and using non-symmetric confidence interval, but what's I think a more effective use of these numbers is to look at odds ratios. We have 4 numbers that we can summarize into 1. So odds ratio for C4 equals 2, given C3 equals 2. So C4 equals 2 versus C3 equals 2. So that's probability 226 divided by 764. That's the odds of staying in the middle class, staying in class 2, for poverty equals 1 divided by the similar ratio for poverty equals 0. So odds, 2 odds divided, giving us the odds ratio 2.27. And for a second, let's go straight here to the interpretation. The odds of staying in class 2 versus moving to class 3, that's not something we want. That's an undesirable outcome. Is 2.27 times larger for those in the poverty group than those not in the poverty group. So that's odds ratio, summarizing 4 numbers up here. And just for fun, you can check then the odds ratio is 2.27. The log of that is 0.82, which is the estimate of G2 corresponding to the notation in our transition tables expressed in loaded form. So e to the power of G2 is 2.27, but G2 itself is 0.82, where G2 is C4 class number 2 regressed on poverty. Now this is comparing to the last class, whereas Mplus instead focuses on or also adds the output using the diagonal class as a reference class. So then you divide these numbers a little bit different. You take 0.764 divided by 2.226 instead of the other way around, and 0.881 divided by 0.115, and you get 0.44. So that's the odds ratio for moving to class 3 versus staying in class 2. Moving to class 3 versus staying in class 2 is lower for those in poverty than those not in poverty. So the odds is 0.44 lower for those in the less fortunate group. Now the odds ratios and their confidence intervals are given under the heading Covariate effects on transition probability odds ratios. You note also that for a regular LTA that we're talking about on this slide, 5 out of these coefficients for C2 through C4 in poverty are significant. So most of them are significant. So in this case, we really need those effects included. And that manifests itself by these numbers being different. This being higher than that, this being lower than that. Now, if you do the same thing for RI-LTA, this is model 6, that is run 8, the output from run 8. Once again, C3 to C4 transitions, and poverty equals 1, poverty equals 0, looking at the same type of classes here and here, we see less of a difference between poverty equals 1 and poverty equals 0. And in fact, only 2 of these C2 through C4 effects that indicate effects of poverty on the transitions are significant. So there's less of a need to include those effects. And one could say actually that most of the effect of poverty is on the random intercept factor f. That is not an effect on the transitions themselves. And the effect of poverty on f indicates measurement non-invariance with respect to poverty. So poverty explains the random intercept factor f, that is the individual differences in the response probabilities coming from f, and f then being the time invariant measurement non-invariance, which is another way of looking at it. Looking again at the outline here on slide 76, we're now going to turn to investigating measurement invariance across individuals, a key concept here. We're going to look at both multiple group analysis and an approach where we have direct effects of covariates on indicators to study the measurement non-invariance. Now, the multiple group approach uses the known class option in mixture modeling. So that adds one more class. It's a known class, but it's still one more class, which makes computation slower. So 2 groups makes us have twice as many cells in the cross classification of all the latent classes. The measurement probabilities are given for each known class under the heading results in probability scale, as we will see. An alternative is to use the direct effects of covariates on latent class indicators. And that's faster than using known class. For regular LTA, it's about a factor of 2, and it's a factor greater than 10 for random intercept LTA. The advantage there is that you get significance for each covariate indicator pair given directly through the estimated direct effects. Now, the calculator can give the measurement probabilities for any combination of covariate values, and we'll take a look at that. Here is the picture for direct effects of covariates on latent class indicators for the RI-LTA model. And the only difference for regular LTA is that it excludes the F factor up here. So you have an X variable that is allowed to influence each of the observed indicators directly, so that even conditional on a certain class, you have different response probabilities as a function of the different X values. In this case, we have RI-LTA, we have the F factor up here, and note that in this case you would not have F regressed on X as we saw in earlier pictures. It's not needed and should not be included because that's not an identified model when all direct effects are present. So we allow for differences in response probabilities within class as a function of X. We cannot also have an effect of X on F, so that essentially F would have 2 different means, one for poverty and one for non-poverty, for instance, and that those different means affect the latent response or the latent class indicator probabilities as well. It's not identified. you can compute the direct effects on the probabilities of the latent class indicators given class using the calculator. So we click on conditional probabilities for the latent class indicators. So conditional on certain x values. And then we click OK, and we get down to the window, the menu options that we've seen before. We want to assign a value, say 1, to poverty and apply. So let's take a look at the outputs for investigating measurement non-invariance here. 10, 11, 12, and 13. So starting with number 10, so that's a regular LTA with poverty as a known class, and where you thereby allow for measurement non-invariance. So the input instructions are as follows here. I should go up here and show you. First of all, there's a known class, P, say, poverty class, 2 different classes corresponding to poverty 0 and 1, in addition to the 4 latent class variables. And here we increase the number of random starts a little bit because it's a more complex model. And then you regress C1 and C4 to C4 on P to allow for different latent class probabilities for the 2 poverty classes. And then you have the usual latent transitions over time, lag 1. And then the specific approach here is the so-called dot approach. So model P dot C1. So we have then 2 times 3 combinations, class 1 for poverty for P and class 1 for C1. 1 and 2, 1 and 3, and then class 2 and 1, 2 and 2, 2 and 3, all with this dot approach. So we look at every combination here in the 2x3 latent class table. And we see then that across, within a certain poverty class, say 1 here, we have the usual differences in measurement probabilities in the thresholds across the classes. But then for the second P class, we allow a different set of thresholds with different numbering. But those numbers get repeated for time point 2 for PC2 with its 6 combinations. But so consistently throughout here we allow for 2 sets of thresholds, so 2 sets of latent class indicator probabilities for each of the 4 time points. So going back up here then, we note then that we don't find any measurement part here. Instead, we will find the measurement probabilities for each latent class indicator and latent class in this part of the output, results in probability scale. And in this case, we have not ordered or reordered the classes, so we just have to find them. So here we have high probabilities throughout. That looks like the highest class. So C1 is the highest class, and C2 is the middle class, and C3 is the low class. So that's for P equals 1, and then you get corresponding values for P equals 2, and you can piece these values together and put them in a table to report. Now let's look at doing this using direct effects instead. So that's output number 11. So here's the faster approach to do this. You have same 4 latent classes, so you don't make any slower by adding a known class. And then you have the usual latent transition part of the model and the regression on the poverty covariate. And now we're going to, if we jump to model C1 here, we're going to allow for direct effects of poverty on the latent class indicators. This is at time point 1. And so they are allowed to be different across the latent classes. But they are allowed to be, they're held to be the same across time points. So the direct effects are the same, have the same numbering across time points, as you see here. So that's just staying with the idea that we have measurement invariance across time, but not across individuals. That's the same assumption that we work with in the known class approach. That also holds the direct effect of non-invariance equal across time. Of course, you don't have to have these equalities across time points for the direct effects. And you could investigate that model if you're interested. And here's just a little quirk. You have to, in the overall part of the model, fix these effects, all of them, from the first item at the first time point to the last item of the last time point at 0. It's essentially opening up a parameter array that you're not using in the overall, but that needs to be open to be accessible in the model-specific, time-specific part of the model. So in this case, we actually have a measurement summary given to us, so that's another advantage of the direct effect approach. Here you have them for time point 1, and that's actually evaluated at the covariate sample means. So that's just a convenience feature for you to check which order the classes come in here. And we see that this is the lowest class, and this is the medium class, and this is the high class. So you get that help. But if you really want to look at the details of how the measurement probabilities vary as a function of the covariate values, you should go into the calculator. So then you go here, look at this part of the menu and assign the value 1 and apply and say OK. And now come the measurement probabilities for poverty equals 1. And here again, you see that in this case, we have a slightly different order of the output. We have the medium class here, the low class here, and the high class here. So this is the more precise estimation of the measurement probabilities, not an average over the poverty values, but actually specific to the particular value, poverty equals 1. Let's see. We go out of that and take a look at a final, or another rather, run, which is the RI-LTA version of the direct effects approach. And that's the one I recommend for RI-LTA. I don't recommend the known class approach there. So we have the 4 latent class variables. Here we have reordered the classes, and since we have direct effects here, it's a very complex model with a lot of parameters, and we want to have as much numerical precision as possible, so we have integration equals 30 here. And the overall part of the model, we have the measurement of the factor, random intercept factor. You have the transitions here. You have the regressions of the latent classes on the poverty. But we do not include F on poverty because it's not identified, as I mentioned. And we still have the fixing at 0 in the overall part of these direct effects. And then same specification as for regular LTA. The direct effects here are allowed to vary across classes, as are the regular thresholds, but are held equal across time points. And all we want to do in this run really is to check the log likelihood and the BIC. And we'll take a look at a summary of that later on. I'm not going to show you output 13 for the known class version of RI-LTA, measurement non-invariance, but it is on the website for Webtalk number 2. On slide 80, we summarize the various kinds of analysis that we've done to investigate measurement invariance and non-invariance for poverty. We have a series of models here that we're listing, both for regular LTA and for RI-LTA. The first model that I showed you in output 10 was using poverty as a known class. And we need to adjust that run, the log likelihood and the BIC, because the introduction of known class adds to the log likelihood in a way that would make it not comparable to the direct effect approach. So we do this adjustment here, which is using the probability of the proportions of the known class categories. So it's an adjustment of this value to the log likelihood, which gives us these values on the second row, which are the same as if you take the attack of direct effects from covariates, have a covariate instead of a known class, and have direct effects to the latent class indicators. You see you get the same likelihood and the same BIC value here. And that's run 11, output 11 that I showed you. And then you want to compare that to having no direct effects, so perfect measurement invariance. And we see that testing those two models against each other with 15 degrees of freedom gives a very high chi-square value. So clearly you need to include the direct effects. This more general model is the one to go with. And it has that BIC value. Now turning to RI-LTA, the direct effects model was output 12. And you have these values for the log likelihood and BIC. And then no direct effects model is the same as we had model 3. Model 3 rather is the same as model 6 on slide 71. So here now, if you compare these two models, they're clearly nested. You have 14 degrees of freedom and chi-square is 28. And so that's not a really strong signal. That's a p-value that's smaller than 0.05 but greater than 0.01. So I'm saying here question mark in choosing between the models, particularly since the no direct effect model has a considerably better BIC. So you may want to go with the no direct effect model for RI-LTA in contrast to regular LTA where you had to use the direct effect model. And I'm concluding here at the bottom, in RI-LTA the random intercept factor takes care of measurement non-invariance that is time invariant. Direct effects are not needed. Here are the results from the multiple group analysis. Can also be obtained from the direct effect analysis. Regular LTA, RI-LTA, poverty equals 1, poverty equals 0. And you see that there is a clear difference. You have much lower probability of getting even the letter recognition item right in class 1 for poverty equals 1 compared to poverty equals 0. Much higher probability when you're not in poverty. Same at the end here for words in context, much higher probability for poverty. Whereas the general structure of the three classes holds up. That is, fewer items are likely to be correct for the lowest class, more for the middle class, and most for the high class. You see that pattern for both poverty groups. And actually for RI-LTA, you have quite similar features if you insist on measurement non-invariance here. Quite similar features to regular LTA. Low, higher here, lower, higher here. But as we said, we didn't find it totally necessary to allow for measurement non-invariance for RI-LTA. On slide 82, we take a closer look at studying measurement non-invariance by direct effects. And we look at the covariate effects on the latent classes and the class sizes. We're going to do this for regular LTA. So in the top panel, we have no poverty covariate included, and we have these class sizes for fall of kindergarten and spring of first grade. When we add a poverty covariate here, assuming measurement invariance, so no direct effects, here are the class sizes that we get. They remain very similar to the ones in the top panel. So here we don't really see a change in class sizes by adding the covariate. So that seems like a success story. And we look at the regression of C on poverty. I take the first C, C1 only here. And here we have the positive significant effect, that is relative to class 3, the most successful class. Probability of being in class 1, the lowest class, is increased by being in a poverty group. For the second class, the effect is insignificant. So we would call this a success story here. We have agreement with the class sizes in the case of no poverty covariate. But if you look at the bottom panel, where we allow for measurement non-invariance, that is, in this case, all direct effects, we get these class sizes. And I should add that the interpretation of the measurement model is the same. So if you look at, for instance, this, the C4 class size for class 3 is 0.22 instead of 0.805. So in the spring rather, in first grade, you get a much lower probability estimate for being in the highest class than what you got when you assumed invariance. And we can note also that RI-LTA with measurement invariance has insignificant effects of poverty on covariate, whereas here we have significant effects, and RI-LTA did not need measurement invariance. But the conclusion here is that even though we think this approach of adding the covariate is successful, that is, doesn't change the classes, the truth is that we have so much measurement non-invariance as gauged by direct effects that the conclusions will be incorrect. On slide 83, we repeat the results that we had on the previous slide at the bottom. They're repeated here at the top. Now let's try multi-step analysis. We're going to call this analysis a one-step analysis, the standard analysis where you do just one analysis. Here's a two-step analysis which has been proposed by Back and Kua in Psychometrica. So what you do here is that you fix the measurement model from the run without covariates. That is, you fix the thresholds in this case, whereas you let C on C regressions be free to be estimated, and C on poverty covariate, to be free to be estimated. Now, if you look at this, it looks very much the same as the middle panel on the previous slide, the same class proportions and the same significance, non-significant pattern. So once again, we might think that that was a successful two-step approach. But it does not take into account the measurement non-invariance that we take into account in the top analysis, which has quite different proportions again, and a different pattern of significance. Here we have significant effects also for the second class of C1 where it's not significant here. You could try to add direct effects to the two-step, but since we have so many direct effects, that really does bring us back to just doing one step. Now at the bottom we also have a three-step BCH approach, which we describe in Mplus Web Note 21, once again assuming measurement invariance. And once again, the results are quite different from what I consider the correct results, the one step with all direct effects included. On slide 84, I tried to conclude. First, by noting that direct effect modeling is important because we want to allow for measurement non-invariance. If you model it, you're dealing with it correctly. If you ignore it, you introduce item bias, differential item functioning, and distorted results, particularly in the C on X part, which is the important part. So we advocate including the direct effects and exploring which ones are significant. Now that can be difficult when you have many covariates, because you had then so many direct effects, so that you have a very flexible model, too flexible perhaps, so you have a very bumpy likelihood that needs many random starts to replicate the best log likelihood. Now there are alternatives that are simpler than that you could try. You could try to regress one latent class indicator at a time on all the covariates, or use just a few key candidate covariates, like we did with gender in the dating example of the Psych-Methods paper that proposed RI-LTA. Now, multi-step methods then, what should we say about them? I would say that they are risky when there's measurement non-invariance, because you risk a bias in the C on X estimation. And that's been studied in several places. Vermont did a paper in 2010. We did a web note that turned into a paper in the SEM journal. And we did a simulation study, which is given in section 5.1 of the web note, which has fewer typos than the published paper. So we have a simulation study there where bias for C on X was found in cases with low entropy, that is low class separation, poor measurement model in other words, and many direct effects. A low entropy in this case was 0.6, high entropy 0.9. And this was also pointed out in this Jansen et al. Paper more recently in the SEM journal, where they also pointed to the fact that smaller sample sizes tends to also produce more bias for C on X in combination with direct effects. So what do you conclude here then? Well, you can say it in a snappy way by saying when you really need multi-step approaches, it doesn't work. And when it works, you don't really need it. So what do I mean by when you really need it, it doesn't work? Well, when you really need it is when the class formation changes, when the class percentages change. And that tends to happen when you have many direct effects, when you have a poor measurement or weak measurement model, that is a low entropy, poor separation between the classes, and low sample size. And those are exactly the situations where it doesn't work well. So when you really need it, it doesn't really work. Now when it works then, I would say that you don't really need it. You don't need it when class sizes don't change when adding covariates. And they don't change because of no or few direct effects, or high entropy, that is a strong measurement model, and a large sample size. So in that case, you probably don't need it, but that's a case where it would work. So there's a bit of a dilemma. You should be careful when you do multi-step approaches to study C on X in the case where you suspect measurement non-invariance. And you know, when you have so many covariates as there are in many real data applications, it's likely that several of them, gender, age, ethnicity, etc., do have effects on the measurement part. That is, there are direct effects most likely. And if you leave them unexplored, and then you might run into these biases that I've shown here. Finally, let's take a look at the random intercept model a little bit closer from a measurement non-invariance perspective. So for a binary latent class indicator, at a certain time point for a certain class, the logit of the probability of getting this item right, given a certain class and given a certain factor value for individual I, is the negative of the threshold tau plus lambda times the factor value. And the lambda is the factor loading, and the factor value varies across people. So a high logit value implies a high probability of getting the item right, and you would get a high logit value for positive lambda and a factor that's greater than 0. So above the mean. In the presentation of the measurement probabilities, the random intercept factor is integrated out, collapsed over. So we consider the overall conditional probability of U given C, not given C and F. So we integrate out F. But individuals with different F values have different conditional probabilities, as we see in equation 1. So that's a very explicit way of saying that the probability of getting an item right is not only a function of latent classes, latent class membership, which is captured by the thresholds in a certain latent class, but also of the individual's factor value. So that's a classic definition of measurement non-invariance. So the random intercept factor can be seen as capturing the measurement non-invariance, and I think that's why we didn't see as strong of a need to allow for direct effects in a covariate approach when we analyzed the random intercept model. On slide 86, I actually computed values for the measurement probabilities at different F values, minus 0.5 plus 0.5. So that's with a mean of 0 and a variance of 1. That's one standard deviation apart. And this is using an analysis without a powered covariate. And you see this pattern for a low reading proficiency, you might call it. You have the low probability of getting the easiest item right, whereas with a high proficiency, you have a high probability. So that's a pattern we've recognized now. Same thing for the hardest item, much higher probability of getting it right for a high factor value. And I compute this simply by inserting different function values here and just computing that logit by hand. Now, if you do an RI-LTA here, regressing on poverty, F on poverty, and look at the measurement probabilities for the poverty group and the non-poverty group, we find a very similar picture down here as we found up here. Low probability of getting the easiest item right in the lowest class, moving to much higher value, not exactly the same but higher, and same feature for the hardest item. So you can see then that this is, what I mean by this is an illustration that the random intercept factor, its variation across individuals, capture the differences in measurement probabilities for the poverty versus non-poverty group. It captures much of the poverty non-invariance, at least the time invariant part. And it is strongly related to poverty. In this analysis here, we regress f on power t, and we get that strong effect that we saw earlier. So f can perhaps be viewed as the reading preparedness dimension. And by having that dimension, we are already capturing measurement non-invariance, as we see here, and therefore don't need direct effects as much. Now we turn to the special topics shown on slide 87 in the outline. We're going to talk about 3 different topics: modeling stationarity of transition probabilities, mover-stayer modeling, and then distal outcome modeling, which is the biggest topic that we'll spend more time on. On slide 88, we're describing how you model stationarity of transition probabilities. So here on the left, we have a transition table for time point 1 to time point 2, C1, C2. It's given in the usual loaded parameterization of chapter 14 in the user's guide, and that we discussed before. And then we have another transition table for transitioning from time point 2 to time point 3, so C2 to C3. Now, if we want the transition probabilities to be the same across time, we want the loaded parameter values to be the same across time as these 2 tables show. So how do you model that in Mplus? Well, in the overall model, you refer to first here the intercepts, which is what we have on the bottom row of the transition table. So A1 here is C2 number 1, and that A1 should be the same as the A1 in the rightmost table. So that's C3 number 1, A1. So we hold those equal and label it A1 very pedagogically. And then we do for C2 number 2 and C3 number 2, take a look at the other intercept, held equal as well, and labeled A2. We might want to use it for some other calculations. Then we have C2 regressed on C1, which has to do with the B coefficients here. There are 4 of them. We just number them B1 through B4. We could call them B11, 21, 12, 22 if you wanted to, but this makes for a nice list. And those should be held equal to the B parameters on the right. So we give the same labels here. And if covariates are involved, their effects have to be held equal across time as well. Now, this stationarity can be tested. You could do this run and then do the run where you don't hold these equalities, so the regular transition modeling, and compute the log likelihood difference times 2, so we get a chi-square log likelihood ratio chi-square. That's one way of doing it. Another way is to run the model without stationarity restrictions and use model test to see if we have equality of these coefficients. So that can have various substantive reasons for being of interest. Simplifying the model, it simplifies the model certainly if you find that stationarity holds. And it could be interesting to see, for instance, if you have stationarity for certain time periods but not for others in transition analysis where you have many time points, say 4 or 5. Okay, turning then to slide 89, we're going to take a look at mover-stayer modeling. And I should mention that this is described in detail in the user's guide, example 8.15. So here we add a latent class of stayers who have 0 probability of changing class. So probabilities 1 on the diagonal and probabilities 0 in the other elements, the off diagonals. I went through and talked about that more in Mplus Webtalk number 1 and applying the mover-stayer model to different kinds of data sets, not only the reading data. So with regular LTA, no covariates, we have the no mover stayer component model, which we have looked at before, 35 parameters. Now we add a mover stayer component, and it has 38 parameters, so 3 more. I'll tell you how we get to 3 more in a second. And you see then that the log likelihood improves a little bit, and you get a big that is worse, however. So and only 6% stayers in this case. So probably with 3 degrees of freedom difference here and a log likelihood difference of 2, which you multiply by 2 to give 4, it would not point to a mover stayer model being needed here. Note, however, that you are not allowed to do a chi-square difference test here, because these 2 models differ by adding a new latent class variable, the mover stayer latent class variable. You don't know how many individuals are in this stayer class, so it's a parameter that you have to estimate. It's a probability that you have to estimate, and in the top model here, that probability is 0, so it's on the border of the admissible parameter space, and therefore chi-square doesn't work. Nevertheless, the log likelihood difference seems to be small relative to the degrees of freedom, not degrees of freedom, but rather the difference in number of parameters, and the BIC is worse. And we only have 6% stayers. So in this model, for these data, I should say, it doesn't seem like it's reasonable to have a large stayer component because of the nature of development over time. As we saw earlier, I think there were a small fraction, 91 individuals, who stayed at the low class throughout. Okay, now turning to RI-LTA, no covariates, we have the no mover stayer component with this BIC, which is considerably better than the BIC for regular LTA. And the mover stayer, if you try that, you get 0% in the stayer class. So it's clear that mover stayers, that model is not needed. And that can be explained to some extent by the random intercept factor. If you have large positive loadings on the random intercept factor, which we talk about that factor in terms of reading readiness, perhaps. So large values on the factor tends to keep you in the same model over time more often than, for instance, if you have factor values around 0 or small loadings. Similarly, if you had negative, because the a high factor value together with a large positive loading increases the probability of answering each item correctly. So you tend to be moved towards, or be placed in high classes. And the opposite then is the negative factor value keeps you at a lower probability of answering the items correctly and tends to keep you in the lower classes. So to some extent, mover stayers is picked up by the random intercept factor RI-LTA, and that was also the case in the other examples that I mentioned that were discussed in Webtalk number 1. So let's look though at the input here, and this corresponds, like I said, to User's Guide example 8.15. We're going to use then the parameterization equals probability, which is described in the User's Guide on pages 560 and 561. There are 3 different parameterizations here with mixture modeling and transition modeling, and this is one of them, which is convenient when you have mover stayer modeling. So in the overall model then we have then a new latent class variable C, So that represents movers versus stayers. So we estimate one parameter there. And then we say C1 on C. And I'm not sure that everyone would do that, but I think it's important to say that the starting point of your time series, probability of being in the three classes at the start, fall of kindergarten, can be different for movers and for stayers. So there you have one extra parameter for being in the stayer class and two more parameters for C1 on C, because C1 has three classes. We then have two slopes in that relationship. So that's 3 parameters total, and that gives you the difference between 35 and 38. And then for model C, class number 1 is the mover class, say, the regular class. And we have the usual transition, C2 on C1, C3 on C2, C4 on C3. Then we have the stayer class, and that's where it's convenient to work in the probability parameterization, because we want to say that we have probabilities 1 of staying and 0 of moving, and that can be a little awkward to do in the logit formulation, in logit parameterization. Although there is a web note on how to do that. So here what you do then with the probability parameterization is to regress C2 on C1 fixed at 1. So here we're talking probabilities. The probabilities that you're on the upper left, in the upper left cell, is 1, and continuing on the first row, second column, first row is fixed to 0. So probability is 0 of transitioning, and we don't mention the third column for C2 because it's assumed that it is 0, because these two probabilities say everything, and the third probability is determined by the fact that they have to add to 1. So we don't mention the last column. Same thing for the second C1 row. C21 on C12 is 0, and the diagonal element is 1. And then you do the same thing for C3 on C2 and for C4 on C3. So this probability parameterization is quite convenient in this case, but the reason we don't use it throughout is because it's not general. It doesn't generalize to having covariates in the model, and as well as other more complex features of a model. On slide 90 we start with the distal outcome modeling. And the first step is to remind ourselves of how we do distal outcome modeling in the latent class analysis as opposed to in a latent transition analysis. This was discussed on slides 17 to 20 in the early parts of the Webtalk. Slide 91 then, we have odds and odds ratios for two predictors. For an equation, log odds for u, binary variable, as a function of two x variables, a plus b1 times x1, b2 times x2, where the log odds is same as a logit. That is, we do logit regression. Odds ratio interpretation is that the e to the power of b1 is the effect of x1, irrespective of the value of x2, as a benefit of logistic regression modeling. And the odds ratio for the effect of x2 is e to the power of b2. Now the latent class model is one where you have one single latent class variable c, and you have the distal outcome u here, and you have a predictor x. So x influences c and u, and the influence of x on u is the same for all classes C. That is, there's no broken arrow indicating an interaction model, but it's a main effect model here. A logit regression then with x and a latent class predictor C is like this. That is, it is the intercept that varies across the latent classes C, and that's the same as the negative of the threshold, which we call t here. And then we say that the odds ratio effect of x is e to the power of b, that is e to the power of this effect here, irrespective of which latent class we are in, by the rules that we established up here. And the odds ratio effect of the latent class, that is the effect going this way, is expressed in terms of the u odds, that is the odds of getting it right versus getting it wrong, for a certain class, divided by the odds for the last class. And it's not influenced by the value of x at all. Now, slide 92, you have an interaction here between x and c, so that the effect of x varies, effect of x on u varies across the c classes. The logistic regression then is has a slope that also varies across the classes. And written out in terms of thresholds, it looks like this. Just as a reminder. So turning to slide 93 then, we're going to get back into the reading example and take a look at a distal outcome predicted by an LTA. So we have the 3 classes again here and the 5 items. And we remind ourselves of the pattern of probabilities. And we're going to focus on the site item, which is a clear indicator of being in class 3. That is, the probability of getting that item right is very low in class 1 and class 2, but very high in class 3. So that's a good item to discriminate among classes 3 versus the other 2. And that's what we're saying in this bullet here. So one question one could have then, what can we say about the likelihood of mastering the site item at spring first grade, the last 4th time point, based on development from kindergarten fall to kindergarten spring? That is, by the end of kindergarten, what can we say about the likelihood of mastering site 1 year later? Here's the model diagram that we can draw. We have then 2 time points, fall kindergarten, spring kindergarten. We have the poverty covariate, which influences the class probability at the starting point and at the ending point. That is, it influences the transitions. It's a main effect model because we don't have C1 influencing poverty's influence on C2. So the transition follows the main effect model. You could have the interaction effect model too, but for simplicity we choose this model, and it's also a better fitting model. Now the distal outcome site 4 at the 4th time point is influenced by poverty and by C1 and by C2 and an interaction of C1 and C2 as indicated by this broken arrow. So it's in effect influenced by the transition paths. On slide 95 then we can get back to looking at different transition paths. Here we have 3 rows corresponding to 3 transition paths. So we're talking about fall kindergarten, spring kindergarten, and individuals can be in class 1 fall and stay in class 1 spring, or go to class 2, or start in class 2 and stay in class 2. Other combinations are so much less frequent that we can ignore them here. So those transitions have 21, 44, and 20% respectively in this sample. So then we can ask ourselves, well, for those 3 transitions between the latent classes, what's the probability of getting the site item right in the spring of first grade? If we look at those in the poverty group, we see that the probability of getting the item right is lowest when you stay in class 1 in kindergarten, considerably higher when you move up to class 2 by the end of kindergarten, and highest if you start in class 2 already in the fall of kindergarten. So you have a clear distinction here in the probabilities. Now with poverty equals 0, you have a much higher probability of getting that sight word item right in all three of the transition paths. So that's higher than that, this is higher than that, that's higher than that. To do this kind of modeling then is an exercise in using this dot approach, which refers to a combination of latent classes. I'm going to show you the Mplus script for that in detail. Now once you've done this analysis, you want to do a check to confirm that the latent classes stay the same even after adding the sight 4 item. And they do in this case. Now the probabilities for sight 4 that I show up here at top right, they can be calculated via thresholds and the slope in the regression of sight 4 on poverty. Using the model constraint command as I show in the next slides. It's not available via the calculator that we talked about earlier, because this is the case where the items are influenced, where the sight item is influenced by more than one latent class variable, you know, C1 and C2. Here's the Mplus script excerpt. So you have C2 on C1, and C1 and C2 both regressed on poverty, and we have sight regressed on poverty as well, and we give it a label which we may use later on. And here's then the essence of the dot command. So inside the overall part of the mixture model, you refer to a combination of classes, C1 dot C2. So you have C1 number 1, C2 number 1, and then you have C11, C22, C11, C23, C12, C21, etc. down to C13, C23. And within each of these combinations, you have the usual threshold labeling. So when you move from C2 class, when you stay in C1 class 1 here, which you do here, here, and here, the first time point thresholds labeled 1 through 5 are held equal, whereas the C2, when the C2 classes vary, which they do, the thresholds for the second time point vary across those C2 classes as we usually have them do. We want the thresholds to vary across these classes, but it's only the thresholds for time point 2. For time point 1 thresholds, we have equality 1 through 5 here. And then similarly throughout the whole script. So that's a dot command, very flexible approach where you can specify equalities in any which way you want. Now regarding the model constraint statements to compute the probabilities, you have for poverty equals 1, the probability is 1 divided by e to the power of the minus logit as usual. Well actually you should say divided by 1, I have it correctly here, 1 plus 1 to the 1 divided by parenthesis 1 plus the exponent of the logit, negative exponent. The logit is the threshold plus the slope b that we labeled before times poverty. And since the logit should be negative inside here, you have the positive threshold minus the slope b, and b times poverty equals 1 in this case. So here you have the probabilities for the first row in the transition table, for the second row, and for the third row, the first index pointing to poverty equals 1 as opposed to 0. The odds ratios for the effect of transitions on site 4 then can be explained this way. So we're interested in the effects of transitions on site 4. We can compute them in line with those slides 19 to 20 generalized to a multiple time point situation, but they're already given in Tech 15, thankfully, because there's a lot of model constraint statements you would have to come up with otherwise. It's given under the heading Latent Class Indicator Odds Ratios for the Latent Classes. It's not a output segment that we looked at before. I don't use it very often. I look at the probabilities of the latent class indicators as a function of the latent classes instead. But you could have odds ratios results also for those relationships between the classes and the indicators. Now let's look at the odds ratios for the different transition examples, the 3 that we looked at before. You have 1,1, that is staying in class 1 through kindergarten, 21% were there, versus 1,2, 44% were in that better performing transition. That has odds ratios 0.150, which is significantly less than 1, which makes sense. We have a very much lower odds for staying in, let's see if I say this correctly, much lower odds for staying in the starting class versus moving on. That's what we hope to be the case. That is better, higher probability for moving on. And we see that. Now you may instead want to compare moving on versus staying, but that's not printed in the output. It is, however, obtained as the inverse of this odds ratio and the inverse of the limits, switching their order, and then you get odds ratio 6.67, which is greater than 1. The confidence interval does not include 1. So in words, if you progress from class 1 to class 2 by end of kindergarten, your odds of mastering sight words at the end of first grade is almost 7 times higher than if you're still in class 1 by end of kindergarten. So you may want to read that and think about it. It's a lot to take in. So it's better to move on than to stay, which is what you want to see. Now, what about being in class 2 already from the beginning and staying in class 2, 20% take that path, versus staying in class 1? Well, that is a very high odds ratio of 33. Clearly different from 1. So it's much better to be able to stay, to be in class 2 already, even if you stay there throughout kindergarten, even if you don't move on. Now then you can ask also, what about that transition path that is staying in class 2 through kindergarten versus moving up to class 2? Well, that's odds ratio of 4.9, significant, so that it's better to have started in class 2 than just having ended in class 2. So that's kind of interesting, and it tells you a little bit of the story of transitions. Now we also have the odds ratio for the effect of poverty on site 4. Up here we talked about the effect of the C1, C2 classes on site 4. So now we're talking about, if you go back 4 slides, we're talking about this effect here. And that's 0.514. So if you're in poverty, you're about half as high odds to get site 4 right. And that's irrespective of class by this model, as given under the heading Logistic Regression Odds Ratio Results. Finally, then, in this part of the talk, we can ask the question, does the fall kindergarten status matter? Or is it only where you end up in kindergarten that's important for how you do on the site item at the end of first grade? So we can take a look at modeling the effects of latent classes on site 4 here. First model is the model we talked about and that we show in the picture. We have a C1, C2 interaction effect on site 4, and it has these number of parameters, log likelihood and big. Then you can contrast that with a simpler model where only C2 influences site 4. So you don't have that arrow or this arrow. And that gives you 31 parameters. It's 6 fewer. And the way you think about this is that in this model you have 9 different thresholds for site 4, 3 times 3. Whereas C2 only, you have only 3 thresholds. So 3 minus 9, or 9 minus 3 rather, is 6. So that's the difference in number of parameters here. And that gives you a considerably worse log likelihood and a worse big. And you can actually then, in this case, test model 2 against model 1. Chi-square with 6 degrees of freedom, 56. So you would reject that model in favor of model 1. So it's not only the ending status that's important, it's having to do with what happened before then also. Now here's an interesting model 3. C1 and C2 main effects, so not the interaction, but just the main effects, that is this arrow and this arrow. Then you have 33 parameters, and I'll get back to the number of parameters in a second. That gives you a slightly worse log likelihood value, but only 1, so multiply by 2 gives 2 with 4 degrees of freedom difference. So testing model 3 against model 1 gives you, with 4 degrees of freedom, chi-square value of 2. So not significant. So we go with model 3. Model 3 is also more parsimonious, fewer parameters than model 1, and it has the best big here. 559 instead of 590 something. Now, so this means that we have, in this model, we actually have 5 thresholds. So 9 minus 5 is 4. So that's the number of, the difference in number of parameters. We have 5 parameters, and this is a little tricky because one can see this regression, that is site 4 regressed on C2 and C1. One can see C2 and C1 as each consisting of 2 dummy variables for representing the 3 classes. So site 4 regressed on 2 sets of 2 dummy variables, and that regression has an intercept, and it has a slope for the C1, the 2 C1 dummy variables, so that's 2 more parameters, and 2 slopes for the C2 dummy variables, so that's 4 plus 1, 5 parameters total. If you add interactions then between these dummy variables, 2 times 2 is 4, that's 4 interactions plus the 5, gives you the 9 parameters, that is the 9 thresholds that we have in the transition model. So that's kind of tricky to deal with, but that's how it goes. And we're going to see how you model this in Mplus. But anyway, the conclusion is it matters where you start in the fall of kindergarten, but it's not the transition that matters so much as where you were at C1 and where you were at C2. So thinking about this, so we're saying essentially then that the effect of being in class 1 kindergarten, that kindergarten status effect is the same whether you move to class 1 or if you move to class 2. So the movement doesn't matter, it just matters where you started and where you ended, which is kind of an interesting situation. And in other contexts, in other real data analyses, you might find that it's the movement that also has an effect. And this is, by contrasting these 3 models, you can see how that plays out. And so these 3 models are of interest to study in detail, and we'll do that in the next segment 20. Returning to slide 99, which is the slide we ended on in segment 19, we consider three different models for the influence on the distal outcome. The first model has a C1, C2 interaction, and that's the model that's shown in the picture up here. C1 and C2 influences the distal outcome site 4, and their interaction is marked by that broken arrow. Model 2, only C2 influences the distal outcome. In model 3, we have C1 and C2 main effects, but not the interaction effect. Now this is for regular LTA, but you could consider this also for random intercept LTA, where you have a random intercept factor up here influencing the items at the 2 time points. And in that case, the poverty covariate may well influence F, the random intercept factor as we've seen, and the random intercept factor may also influence the distal outcome. The C1, C2 influence on site 4, however, remains the same. That's not part of the measurement model. Yeah, and you can also consider a multi-step procedure where in the first step you do not include the distal outcome, just to ensure that the solution that you get by analyzing this part stays the same when you add the distal outcome. With this binary item, nothing changed in that regard, hardly at all. But it could be the case that it changes if you have, say, a continuous non-normal distal outcome. So here it is. RI-LTA version is possible. I don't have much experience with that at all yet, but I think it should work all right. And then the multi-step approach here. So now let's take a look at the outputs for these three models, which is outputs 14, 15, and 16. Actually, we don't have to look at model 1's output 14 because that has already been described on slides 96 to 97. So let's go straight to model 2, which is output 15. So model 2 is the C2 only approach. How do we do that? Here you have it. The input instructions then are again using the dot approach. So you have C1 number 1 dot C2 number 1. And the only thing that changes here is how we deal with the thresholds for the distal outcome. So they change over the C2 classes, which is what we wanted. But when we change from C1 1 to C1 2, we repeat the labels that we have at the top here. T11, T12, T13 repeats T11, T12, T13. And for C1 class 3, same thing, T11, T12, T13. So that shows the flexibility of working within the dot approach in that framework. We just can change the equality structure. Now let's take a look at model 3, which is a little bit more complex. The input instructions once again use the dot approach, and here we actually stay with the original 9 thresholds: 11, 12, 13, 21, 22, 23, 31, 32, 33. So 9 thresholds corresponding to each cell in the 3x3 transition table between C1 and C2. But we add a model constraint section here. So we're going to put constraints on these 9 thresholds and express them in terms of fewer parameters, which represent a main effect model. So here are the parameters. A is going to be an intercept, B's and C's are going to be slopes. So the way to think about this is that C1 and C2 give rise to dummy variables. C1 has 3 classes, so we have 2 dummy variables that represent that. and that would be the two slopes for those two dummy variables, b2 and b3. C2 also gives rise to two dummy variables, and those slopes will be called C2 and C3. So this is essentially dummy variable regression. So we have then an intercept instead of a threshold. So we call that A. It doesn't matter which of these cells you actually call A. So then when you go from, you stay on the first row, when you go from column 1 to column 2, you add C2 from the C2 class variable. And then you go to the third column, you add C3. And then you go to the second row, that is class 2 for C1. Then you add B2. And for T22, you keep the same, in the same row, B2, but you add C2. And then for the third column in the second row, you add C3. And then you go to the third row of the C1, C2 table, and you add B3. Third row, second column, you add also C2. And for the last column, you add C3. So those are 5 parameters that you express the 9 thresholds in. So in the model estimation, we're actually not estimating 9 parameters, but estimating these 5 parameters. And you find them in the model results section. So we look at model results here, and then we have the section new additional parameters A, B2, B3, C2, C3. Some of them went big and therefore were fixed. It doesn't matter which high value you fix it at really, but that corresponds to 0 cells, which we're going to discuss further in the error message section. So there you have the values, and that's how we got to the results with 33 parameters and this likelihood value. Now, just from a pedagogical point of view, it could be of interest to try to figure out what an incorrect approach would be. So we want to have a main effect model here. We want to have an effect from C1 and from C2. So why don't we just simply abandon the dot approach and go into the usual model C1, model C2, and mention the site threshold for C1, have it change as a function of C1 classes, and also change as a function of C2 classes rather. Well, it's tempting, and I've actually made this mistake myself, but what this means, the parameters that you mentioned in model C1 are held equal or not changing over the C2 classes. They're supposed to change only over the C1 classes. Likewise, here, parameters I mentioned in the C2 classes are assumed to be equal across the C1 classes. So there's a contradiction here. So we have to remember why this model C1 and model C2 construction was set up in the first place. It is to say at time point 1, here are the parameters that change, and they don't change across time point 2. Time point 2, here are the parameters that change across latent class variable 2's different classes, but not across the classes of C1. That's the standard setup. You could, of course, imagine that C2 thresholds were influenced not only by C2 classes, but also by C1 classes. But then you would not use this construction of model C1 and model C2, which is a simplification, so you don't have to use a more complex dot command that you would otherwise have to use. So this is the wrong approach to take, and it gives the wrong number of parameters. So you will find out that it's not the right way to go. Turning to slide 101, the outline shows that we have now reached the error messages section, which is a fairly long section discussing a little bit about maximum likelihood theory and non-identification matters related to the error messages that you get from latent transition analysis in Mplus. On slide 102, I give some basic information about ML estimation. We maximize the log likelihood function by finding an estimate of a parameter that gives a 0 first-order derivative and a negative second-order derivative. So here you have an example. X-axis is the parameter that varies, and we want to find a particular value that we'll call an estimate. On the y-axis, we have the log likelihood, and we're saying that we want the estimate to be the value of the parameter that gives the highest log likelihood, that is the peak up here. We find that peak iteratively. For instance, we may have a starting value down here, and where we see that we have a positive improvement in the log likelihood, the positive slope with respect to the parameter, and therefore should move to the right to get to the peak, where the first order derivative becomes 0. If we go too far, the first order derivative becomes negative, and we will go back that way. Well, we want to make sure that this is actually a peak and not a valley, and to do that we want to find a negative second order derivative. This is a case of a peaked log likelihood which corresponds to a small standard error. That is a well-determined estimate. In contrast, you have the picture on the right where you have a very flat log likelihood in a large part of the parameter space. So you would get a large standard error, or if this is totally flat, it's a non-identified model, because you have two different parameter values that give the same log likelihood value, so you can't tell which one to choose. Non-identified model. Now the real-world situation here is more complex. We have a bumpy log likelihood, which is known to be the case when you have mixtures. So you have several local maxima here, so you bump up and down, and you want to find the highest peak, not a local peak. So you use many starts. We discussed that more in short course topic 5 on the Mplus website, and show pictures of the log likelihood in slide 116. And not only that, but we have to search for the best estimate in many dimensions. Not only for one parameter, but like for output 12, we will have 63 parameters. So you look for the maximum with respect to 63 different dimensions. That's pretty amazing that this actually works. Turning to slide 103, we want to introduce a key concept of the information matrix. So the ML estimate of the parameter vector theta, say that you have 63 parameters. That parameter estimate has a covariance matrix V of that theta hat, the estimated. That's the I to the power of -1, that is inverted information matrix I. On the diagonal, if you take the square root of them, you get the standard errors. Tech 3 gives this covariance matrix and the corresponding correlation matrix. Now the information matrix can be approximated, can be estimated in at least 3 different ways. In Mplus we do it by using first order derivative products using the MLF estimator, or using a negative second order derivative matrix, which is the ML estimator, sometimes the expected second order derivative matrix, or a sandwich combining the two, which is MLR. That is, you have as bread of the sandwich MLF component, and as the meat of the sandwich the ML component. Now the information matrix has to be positive definite, which means that it has to be greater than 0 in a single parameter case. Positive definite greater than 0 in a single parameter case. The more peaked the log likelihood is, the smaller the parameter estimate and the standard error. That is, the better determined the estimate is, like in the figure A on the previous slide. And when the log likelihood is flat, the second order derivative is 0. So it's not positive, it's not negative, but it's 0. And therefore the parameter is not identified. Or another way to say that is that the model is not identified if two sets of parameter values give the same log likelihood value. That means that you can get different estimates, but they give the same log likelihood, so you can't tell the estimates apart using the maximum likelihood principle. There's also a concept of empirical non-identification. That's for models that are identified in principle, but in certain data sets you don't have enough information to identify at least one parameter. On slide 104 then, we connect up with non-identified models using the concept of the information matrix. A non-identified model has a singular information matrix. Singular means in the single parameter case that it's 0. You know, we wanted it to be positive, but sometimes it is 0. And because the information matrix needs to be inverted, that is 1 divided by I in a single parameter case, it can't be singular because you can't divide by 0. And you see here in this little formula why, because the information matrix, the more information you have, the smaller this value is, which has to do with the variance and the standard error of the estimate. So the more information, the smaller the standard error. Now, technically speaking, a singular matrix has at least one 0 eigenvalue. Eigenvalues and eigenvectors are a way to characterize a matrix. So this idea of eigenvalues is very helpful here to numerically determine when you get too close to singularity, that is, too close to dividing by 0. And that leads us to the idea of condition number. It's a good indicator of a close to singular matrix. It's the ratio of the smallest to the largest eigenvalue. And when it's very small, in this case less than 10 to the minus 10, typically in Mplus, then we numerically determine that the matrix is singular, where 10 to the minus 10 is 1 divided by 10 multiplied 10 times. So very, very small value. During the inversion of this information matrix, or attempt to invert the information matrix, Mplus actually finds the row, that is the parameter, that triggers falling below this condition number threshold. And it prints this parameter with its parameter number that corresponds to the numbers in Tech 1. We talked about 3 ways of estimating the information matrix, and one is the first order derivative product version, and that's a particularly sensitive one, able to pick up singularity and non-identification very easily, and it's always checked in Mplus, even if you ask for MLR. All of this is described in the FAQ that we have updated recently. So let's take an example on slide 105. Simple case of a one-factor model with 3 factor loadings and 3 factor variance. We call them lambda and psi. And we know then that we have forgotten to set the metric of the factor, either by fixing the first loading or fixing the factor variance to 1. In that case, we can change the parameter values by multiplying factor variance by c, a constant, and dividing the loadings by square root of c, and to get the same log likelihood. So we have a whole slew of parameter values, sets of parameters, that give the same log likelihood. So we can't determine what the estimates are from the log likelihood principle. So it's non-identified. Another way to saying that is that the log likelihood is flat in the direction of psi. For instance, all psi times c values give the same log likelihood value. So you can fix psi at any value and you get the same log likelihood. So that's an experiment you can do if you think you have a non-identified model. Fix the parameter that you suspect to not be identified, fix it, and see if you get the same log likelihood as when it was free. That means it was not identified. As an example, say that you do an RI-LTA, but you've forgotten to fix the factor variance at 1, whereas you have all the loadings free and held equal across time points. Then you're going to get this message. Standard errors of the model parameter estimates may not be trustworthy for some parameters due to a non-positive definite first-order derivative product matrix. So that's the MLF check, the sensitive one. This may be due to the starting values, but probably an indication of model non-identification, and the condition number comes into play here now. It's 0.687 to the power of minus 16. So, and then you point to which parameter it is. Parameter 6 is the factor variance, correctly pointed out. But what does this mean? For those of you not used to that notation, here's an example. 0.1 d minus 1 means 0.01, which is 10 to the minus 2, where d means double precision, working with 15 digits. So 10 to the minus 2 is 0.1 d minus 1, d minus 1. Here you have d minus 16. So very small value, certainly lower than the 10 to the minus 10 threshold that we talked about in the previous slides. So this works quite well, picking up the non-identification. Sometimes you will see the message coming out in the first order derivative setting. Sometimes you will see it as described as a singular information matrix. Both of them point to a non-identified model, and we will see several examples of that in the coming slides. On slide 106, I will give you an LTA example with these kinds of error messages referring to non-identification. We start with a simple LTA example, and that's output 2, so it's a run without covariates. And we get two kinds of messages. First one has to do with loaded thresholds that approached extreme values and were fixed. These values imply probabilities of 0 and 1. In the model results section, we note this by having 0 standard errors and 999 in the z-score and p-value columns. We're going to take a look at details of how this happens. The second message has to do with multinomial loaded parameters, fixed again, to avoid singularity of the information matrix. So here we raise the possibility that the model is not identified, but it may be empty cells in the joint distribution, that is 0 probabilities, and we're saying that we fix these 3 parameters. We're going to take a look at the details of that. Both of these error messages are innocuous. That is, there is no problem with this model, but I'll show you how you understand that that is so. So on slide 107, we take a look at the first example, the first error message, the large thresholds and 0-1 probabilities. That has to do with the measurement model estimates. You know, we have these probabilities for the latent class indicator as a function of the latent class they're in. The low class, the medium class, and the high class. And we notice that several of these entries are at the edges of probabilities, zeros here and 1, probability 1 up here. That corresponds to the model results, the estimates shown on the right for classes 1, 2, and 3, that is columns 1, 2, and 3. Here it's shown for C1, but we know that they're the same for C2 and C3. And we see here that site and words in context have fixed values, large values, and 0 standard errors, and 999 for the z-score column. So that's a case then where 15, a threshold, is fixed at a very high value so that the probability is small to exceed it. The probability is 0 down here. We fix it because we know that we get a 0 also if we have fixed it at have the value 15, 16, 17, etc. Doesn't matter. So in that direction of that parameter value increasing, the log likelihood is flat. So we have a singularity problem here if we let it be free. So it's an example really of empirical non-identification, because we know that these thresholds are in principle identifiable with other data. But in this case, when they're used to represent these 0 probabilities, they need to be fixed. So it's an innocuous problem that has more to do with computations than important issues of the model. Now, what about this 0 here? Well, that corresponds to this value. There we didn't have to fix it as such a high value. So we get the standard error and a z-score here. That means that this 0 is slightly bigger than that 0. So it's like 0, 0, 0, 1 versus that being 0, 0, 0, 0, 0, 1 perhaps. But it's the same principle. We just don't have to fix it. For the last class then, we fix the first item to minus 15. That is, the threshold is very low and the probability is 1 to exceed it. So that corresponds to that 1. So once again, it's to avoid the flat likelihood in the direction of this getting smaller and smaller negative, or larger negative rather, going to the left, and we have a 0 second order derivative, and we get singularity if we don't exclude that parameter when we invert the information matrix. The second message have to do with transition probabilities, being 0 and 1. So here's what it said: one or more multinomial lobed parameters were fixed to avoid singularity of the information matrix. And we have these 3 parameters here that are fixed. So if you look at the transition tables, we have C1, C2, C2, C3, C3, C4 here. We note that we have zeros here in the bottom row, but we're saying C2 number 1, that's column 1, and C1 equals 2, that's this value. And the next one, C2 2 and C1 2, that's this value. So why are those fixed and not these? Well, that has an explanation too. If you remember the logit parameterization, in that parameterization you have the intercept parameters A here on the lowest row, and up here you have B slopes. A plus B, A plus B. So the way that hangs together is shown in this slide here. If you look at the model results, the A parameters here for C2 1 and C2 2, so that's A1 and A2 in that C1 C2 table, they're very large negative logit, not a threshold but a logit, means a very small probability, 0. Now that value is not problematic by itself. It doesn't trigger the condition number threshold saying it's singular, but when it combines with the C22 regressions on C1, you see that you have very high values here. So this is, for instance, C2 number 2 and C1 number 1. So C2 number 2, so minus 25.999 plus 26.619 is going to be slightly positive, and that then corresponds to these positive probabilities in the transition table. So it's not triggered by the error message, not triggered by the intercepts, but by the combination of intercepts and the slopes, because you can make this arbitrarily larger, -30, and just make that a little bit bigger, positive, and get the same probability. So you have that indeterminacy and therefore a singularity and need to fix something. And the reason Mplus fixes the intercepts is simply because, the slopes is simply because the slopes come last. If you look at Tech 1, the C2 parameters are numbered 18 and 19, whereas the C2 on C1 parameters are having a higher numbering, 25, 27. These are the B slopes. So the occurrence of the singularity doesn't happen until you get to the B parameters, and they just happen to come last. Now you note here also that the last parameter mentioned here is 35. So 35, and there were 35 parameters in the model. So Tech 1 lists as number of parameters, all parameters, even the fixed ones. And that's also listed in the model fit section. Nevertheless, those fixed parameters do not enter into the information matrix, and it's not part of what gets inverted. So once again, this is innocuous, and all you have to do is take a look at these zeros and ones, and there should be as many of those. I'm talking about these two zeros, never mind the last column that just had to add up to 1. And the third one is C4 on C3, so that's C4 2, second column on C3, so that's 0. That 0 and those two zeros correspond to those 3 messages there that are fixed. Okay, so that's innocuous. Let's go to another example. RI-LTA, output 9. So that's quite a complex model. It's a model with a covariate, and it's an interaction model. And that was a model that we said wasn't really needed. The main effect model was okay. So I didn't even bother to reorder the classes in the natural order that we like for interpretation. The log likelihood is the same whether you reorder or not. Here you have a warning that the sample covariance matrix of independent variables in class 4 is singular. So that's a new message. That's one message that we're going to talk about. And then you have a message about the standard errors of the model parameter estimates may not be trustworthy because of a non-positive definite first order derivative matrix. Condition number very low, certainly lower than -10. And it's a problem of C2, C1, so we know how to deal with that, how to look at that. Probabilities of 0 and 1. And then finally, one or more multinomial loaded parameters were fixed to avoid singularity of the information matrix. And here it's a number of parameters that were fixed, and we're going to take a look at that error message. Then we have on slide 112, taking a closer look at the warning, the sample covariance matrix of the independent variables in class 4 is singular. So here we have the situation that if you have a class-specific regression, as we do in the interaction models, you have C2 on X has a specific slope for each C1 class. Those regression slopes are not identified when the class-specific variance of X is 0. You have to have a variation in the predictor. And the information about class-specific variances and means for covariates is given in text 7. Now this class 4 is the first class where this problem occurs, and it refers to the 4th latent class pattern listed in text 7. So they're listed in the order 1, 1, 1, 1 for the 4 latent class variables, 1, 1, 1, 2, 1, 1, 1, 3, and then 1, 1, 2, 1, the 4th pattern. And then you get sample statistics weighted by estimated class probabilities for pattern 1, 1, 2, 1. And you see that the mean and variance is 0, which means that here there's nobody with poverty equals 1. They're all poverty equals 0 people, so no variation. And that class pattern is, it's not reordered, so I don't know what the interpretation is, but 28% are in that class, but none with poverty equals 1, apparently. So you have to fix that parameter, and that's again an innocuous fix. It just means that we can't estimate that parameter. So that's what we're referring to here. The fixed parameters refer to C on poverty here, whereas the first bullet here and the last 3 have to do with C on C. But it's C on poverty that triggers the message that we talked about. So C on C, you know what to do, what to look for there. But here we have C on poverty. And you see these fixed values in the model results section, and the technical 15 section, final class counts and proportions for the latent classes based on the estimated model, tells you those frequencies. And you see then, well, let me show you in output 9 what you see. So output 9, let's take a look at the model results first. And we have to scroll down to the class-specific regression. So in latent class C11, latent class C12 and 3, we have C2 on poverty, and C21 on poverty, and C22 on poverty. And you see these fixed values, 999, large negative values. So those are slopes that can't be estimated and should not be really interpreted. And we have some more here as well. And as we go down, there are probably further ones here also. It's just that we don't have enough people in the cells, as we will see in a second. So if you then scroll down to Tech 15 and final class counts and proportions for the latent classes based on the estimated model, you see then the latent class patterns C1, C2, C3, C4, and the various combinations here. And you see that many of the combinations have 0 frequencies, 0 probabilities. So that then makes you suspect that, yes, we have 0 people, and or at least too few people to have variation in the poverty covariate. What you might want to do if you really distrust that this is so, you could create the bivariate tables for C1 and C2 and look at that 2 by 2 table and see how many people are in it and see if every cell has a variation in the poverty covariate or not. So that's a little deeper look into the error messages. I hope it was helpful. Turning to slide 114, here are some final comments on these types of analyses. And in my experience so far, I've found a series of advantages of random intercept LTA over regular LTA. It'll be interesting to see how that holds up when you all start applying this new technique. But so far, what I've found is that we get a much better fit to the data. More information is extracted from the data because of the random intercept factor. And there's less concern about the need for measurement non-invariance across groups of individuals because the random intercept factor picks up that type of non-invariance that is stable across time, like a trait factor. And there's less concern about the need for indicator-specific residual correlation across time because to some extent the random intercept factor picks up constant residual correlation across time. And there's also less concern about the need for lag 2 modeling because the random intercept factor allows latent class indicators at different time points to be correlated directly through the factor, not only through the latent classes. And there's also less concern about the need for mover-stayer modeling. Now there are disadvantages. It does require longer computing time in some cases considerably longer computing time, but it is quite possible with modern day computers. It does also tend to require larger samples than regular LTA, but we found it practical nevertheless, and you've seen the reports on sample sizes that I talked about earlier in the talk, and some specific Monte Carlo simulations are shown in the paper in Psychological Methods. Turning to slide 115 then, there are of course model extensions one can consider. First of all, the latent class indicators can be of many different types. We have only looked at binary indicators, but they can be ordinal, nominal, counts, continuous, and combinations of all these kinds. And you can also work with more than one process. For instance, here we have a random intercept LTA cross-lagged panel model. So we have a latent class model here, latent transition model with the random intercept, and another latent transition model with the random intercept here. It's a little heavier to compute because you have two random intercepts, so you have bivariate numerical integration, but it's doable. And it's interesting then to see not only the transitions within the process, but also how class membership at one time point in one process influences class membership in the other process at the later time point. So the typical cross-lag panel regressions. And you can also think of other possibilities, extensions of the LTA. We talked about distal outcomes, but it could be an outcome that's really a process like a growth model or a growth mixture model that you combine this with. And we've talked about intercept modeling here, random intercept modeling, but you could also add random slopes to capture trends of some kind. And of course there's the possibility of multi-level RI-LTA, where you have individuals within schools or other groups, other clusters. You know that here we do the LTA modeling in a wide single level format. So there is then the possibility, of course, to go to two-level model versions of this, and two-level mixture modeling is available in Mplus, so that should be quite possible. Now in this web talk I did not emphasize multi-step methods, but they are certainly useful, and particularly for distal outcomes. Maybe perhaps less so for exploring covariate effects on latent classes when you have measurement non-invariance, as we showed you an example of. Finally then, here's the shocker that latent class representation is perhaps not always the best model for the data. And I discussed that in web talk number 1, where I talked about another random intercept model, but one that's combined with a longitudinal factor model, which is an interesting model that's not used often enough. And that fits these particular data better. So you may want to, for your own data analyses, contrast the latent transition model with a model that instead works only with continuous latent variables, as this model does, instead of the latent classes. Finally then, again a reminder how this web talk can be referred to. It's a YouTube video which can be referred to in that fashion. So with that, we end web talk number 2. Thank you.